Good morning. Welcome to the 5th day of the summer school. Hope you are enjoying it. Today we have Adèle Ribeiro. She's a postdoc researcher at the University of Münster, and she had worked previously in Marburg University, and also she's been graduate student of Elias Barenboim at Columbia University, and now she'll give a talk about the introduction to causal inference. She has extensive work on causal inference applied more to the medical field and other applications. If you're interested in this field, please talk to her, and hope you enjoy the lecture. Yeah. Thank you for coming.
Thank you. Thank you, everyone, all the brave people that's here in the morning. So this is my 5th year already in the school. It's really a pleasure to be here. It's one of the best schools I know. I actually give lectures in many summer schools, and I can say that this is actually one of the best. So it's really a pleasure to be here. And today it's an introduction, so it's a very introductory course on causal inference. The field is very extensive, so if you have interest in a particular topic that I just briefly mentioned, just feel free to make questions here or even after the talk. So, oops, what happened? Okay, so I always want to contrast with AI, right? So what is AI today? So AI is, we have a set of tools, a very powerful set of tools for prediction, and they are mostly based on correlations, mostly, right? We've been evolving, but this is basically what happens. We have a set of variables, some set of predictors or features, as we used to call, and you can try to fit this or fit or learn a model on the set of variables with the goal of predicting some variable y. And as Mario told us in the first lecture, basically we have a layer where we have representation learning, where we are going to learn a set of latent variables, can be a low dimensional set of variables, but in the sense that in the last layer, we will have the classifier or the regression problem where we are going to actually do the prediction. And everything that you are seeing in this picture is with the goal of understanding or learning this probability distribution, which is a conditional probability distribution, and or like learning a model, right, that takes the variables x and wants a prediction for the variable y. But this prediction is going to capture this conditional probability distribution probability of y given x. It's one task. So everything that we've been doing, so for example, in medical diagnosis, we want to know what's the probability of y given a set of patient features. Or in image classification, we want to know if the probability is a dog or a cat, or can be like a cancer in an image, or depending on the entire set of features in the image. In language modeling, we want to see the probability of one token given the set of other tokens we already have. So you see the pattern is all every that we have a probability of a text in speech recognition given the audio. So this pattern repeats ever and ever again. And this is AI for us today, right? So we have remarkable advances in estimating this quantity probability of y given x, including deep neural networks, transformers. We have more GNNs, graph neural networks, and so on. But the question is, do you think that a predictive model like this can explain the world? It's a very philosophical question. What do you think about it? Who says yes? And parts of the world. Who says no? Yeah. Yeah. And why is that, right? So let's say a very simple task. We want to predict, and I always want to put between parentheses here, it's a guess. I want to guess, in this example, how severe is a fire by observing the number of firefighters. So here we have a set of predictors. It's a only one because we are in a very simple example, which is the number of firefighters. Suppose that you look out the window and you see a number X of firefighters, and you want to predict how big is the fire, right? And if I ask you, for example, I see out of the window that I have 100 firefighters, can you guess what's the size of the fire? It's like very small or like very big? We can guess or not? What do you think? Yes, right? So we can guess. And we can create any function to model this problem. In this case, it's just two variables, X and Y. And many times we can have like a very good accuracy in terms of fitting. So here, for example, we have R square of 92%. And every time that we have then a variable that's correlated to our variable of interest, this is going to bring information to make a better guess, to make a better prediction. Doesn't matter if this variable, what's the role of this variable for the variable y, it's going to help prediction, right? Because it's fundamental, right? What's probability of y given x? So if this is different from probability of y, we have x correlated to y, so we have this difference. And x is going to be important for the model of y if this correlation exists. It's better to have this with x than without the x. Simple like that. But this probability is called observational probability distribution. This is important. Then what's the conclusion of it, right? So sometimes we want to interpret the model, and we want to, so we see this plot and we see changing x because of a positive correlation. Changing x, you change our prediction for y in the sense that the less firefighters, the weaker the fire. There's like a positive correlation. You can put like the higher the number of firefighters, the bigger the fire, but it's the same direction, right? But it's changing x, you change our prediction for y. Can I extrapolate and then make a decision based on that? So can we do decision making or reasoning on top of this model? And this is something that for this example, maybe it's going to be very silly, but this is something that humans do. We see a predictive model and want to use the variables that are significant for this prediction for like decision making. But this is a question. Should we reduce the number of firefighters because of this positive correlation? We expect that the lower, the fewer firefighters, is smaller the fire. So should I then decrease the number of firefighters to reduce the size of the fire? What do you think? Obviously not, right? And why? Because this is a misleading correlation. The order we use to model the problem is not the right direction, right? So the size of the fire actually determines the number of firefighters needed, not the other way around. And so what is the difference then between a variable that helps for prediction or that's correlated to our outcome of interest and a causal effect, or a variable that has a causal relationship? So the causal direction is determined by our understanding of the reality. So we need this understanding. So in the example of the firefighters, we know, right, how the things work. And that is a model. I don't know how to model in a parametric way, but we know that X, which is the number of firefighters, is the function of the fire. And the fire itself, it's a function of other variables. I'm calling them U. You can even have some variables that are affecting both. But the variable y is an argument of the variable x, right? Which means here that x is not a cause of y. Y is a cause of x. This depends on what variable is a parameter of a function of the other, right? How you check that? If you replace completely the equation of the x to a constant, for example, since the variable y is not affected by the variable x, we won't see a change. And that's exactly many times what we want to predict. If I make a change in the road, we will see a change in the variable of interest. This is a task for decision making, which is different for prediction. If you want to guess, you should use X. as a predictor for your model. But you cannot change X expecting a change on Y here, which is decision making. So causal inference is trying to answer this type of questions. So this is an example where we start modeling the variable X and Y when the causation is reversed. So we call it reverse causation. It's just that the intuition or the way that you modeled the problem was in the reverse direction. That's just a name we have it. But the quantity of interest here is no longer the probability of Y given X as in AI in the first slide ahead. It's something that we call now probability of Y given do X. So I want to know what's the expectation or the probability of a variable Y after doing or performing a change or intervention on a variable X. So it's a hypothetical intervention, but that's the goal. We would like to know what would happen after changing the world. And in the example of the firefighters, we will see that after seeing or observing a quantity, the probability of Y changes. But after performing an intervention or changing the value of Y, the probability of Y won't change. So there is a new calculus involved that's not using the observational distribution only, but now it's using this quantity that we are calling interventional distribution. It's just this hypothetical intervention that we have. I mean, the intervention exists, but the intervention is hypothetical. You don't need to perform the intervention to then analyze the probability. We have a calculus, a theory that allows us to manipulate distributions in a way that we account the possibility of having an intervention on the variable. All right, so another example. Question, yes, sure.
Example with firefighter.
Okay.
It's like, so like what I understand is like you're saying, like if I change the number of firefighters, that won't change the fire itself. It's gonna be the same.
Yes.
So then we can say there's no like real causation here because I do this thing, but then I see the same thing, right?
Yes.
Yeah. Okay. So my question is, well, actually, like if you think about it, like if you decrease the number of firefighters, the fire would increase in size. So like you would actually conclude, oh yeah, the number of firefighters causes the fire, you know, because like there would be like an inverse correlation. So it would
That's exactly. I mean, there's a temporal effect here. So if you observe the fire before, like you look at the window, the fire is already there. And that amount of fire that's there, the severity of the fire, that moment, I want to model that. I don't want to model after a few minutes, right? So yes, sometimes there is a problem of temporal here that if you model for different resolutions, you would see maybe a change. But yeah, it could be, right? I'm just giving an example. It could be that there is but you see, this example is going to be related to the one that I'm going to give now. And you see that this depends on the reality. I'm not sure the reality is much more complex than two variables, and that's it. So it's possible that we can have a more dynamical
like sometimes it can be more unclear, right?
It's unclear, exactly. I'm not saying that you need to know that reality to actually do causality. This is going to be the conclusion later. And this is important because in causality, we don't expect people to actually model the functions and everything you have in the reality because this is so complex. So if you had that knowledge, there's no causality anymore, like you're done. You solved the problem already, right? We know that if I knew that that's the graph, then I don't need causality anymore. It's done. It's an estimation of a model. And but yeah, the question is how we learn it later.
Good. Thank you.
Sure. Yeah, so now, so you probably are guessing already what's the answer for this slide because of the question, but let's see another example, nurses and patient mortality. So we have now two different variables. X is the number of nurses in a hospital, okay? And Y is the patient mortality. And it's very common to observe in a data set that hospitals with more nurses, the hospital reports a higher patient mortality rate. And my question for you is, what do you think is the model behind it here? would be like, so X here is positively correlated to Y, right? So we have like the higher the number, the more nurses we have, the higher is the patient mortality. Who believes? Who? Yes, you.
Because we have more.
Exactly. So the size of the hospital matters, right? So for example, is Y a function of X? So we have here, I will define more formally what's this object here. This is a causal diagram, but this bidirected edge is a set of variables that we don't observe, could be the size of the hospital, for example, that determines how much nurses I'm going to hire, and also is going to determine the mortality. We are talking about rates, but it's also increasing. Maybe the hospital is more, you have better facility, better installation. So maybe more severe diseases or patients with more severe diseases are going to that hospital. So you have some latent variables that influence in both of them. But could be something that there's no even causation. It's just this, sorry. It's just the set of variables, these latent variables that's affecting both. And it can also be in this other direction, which is now X again. There is a cause of Y. So that's what I believe that it is. So the more nurses you have, you actually have an impact in the mortality, but it's a negative. Like the more nurses you have, the better is the quality of the treatment in the hospital. So you actually reduce the mortality. But because of this latent confounding, you can have like a positive correlation that's higher than the negative correlation. And in the end, you observe a higher correlation, a positive correlation, right? Because the total correlation is the sum of both. So it can be the negative coming from the causal effect plus a positive of these confounding correlations. And when you observe the total correlation, which is what you observe as from the data set, you can see something positive. So, as people mentioned here, the latent variables can include hospital size, the patient severity, some sort of emergency. So, for example, during COVID, we had a lot of hiring of nurses, but it's an emergency. Of course, we have a higher mortality rate there. So, it's important to understand the entire context. You cannot just observe a positive correlation and assume that this is actually the causal effect or the sign of the causal relationship. And this final one, I know several examples, but many times people ask me, what if we have the time component? We will rule out the possibility of misleading associations and actually identify the causation just because we are in a temporal relationship. And I really like this XKCD comic because it tells us exactly an example of that. So I'm going to quickly read. I don't know if you can read from here, but basically, so a guy comes and say, another huge study found no evidence that cell phones causes cancer. And what was the WHO thinking? And the guy was there at his computer, says, I think they just got it backward. And okay, let's take a look. And you see this plot, and you see that first we see a total cancer incidence increasing over time. So there is like the 70s and the 80s. Here you see a very it's an increase of the number of cancer incidents. And a few years later, you see a very a similar pattern for the number of users of cell phones. And it is a correlation over time. First happened the cancer incidence, and then it happens the cell phone users. So it's a correlation, and it happens after some time. And then the guy says, oh, you are not. No, there are so many problems with that. Just to be safe, until I see more data, I'm going to assume cancer causes cell phones. So it's in the direction of the time here. And again, what do you think it's happening here? Like we can model. So first, it's an important question. Do we think the guy is correct about let's wait until seeing more data to actually answer this question? Is it a matter of data here? Who says that after collecting 1 billion samples, we will see the causal relationship? No, okay, good. Mario always says, unless it's experimental data. This is important, yes. So we are talking about observational data. So if you go after explaining or reducing these confounding effects, maybe you see the real causal effect. And yeah, it could be that the cell phone users causes, the use of the cell phones causes cancers, can be the other way around, can be just a confounding relationship, which probably is what's happening here. We don't know the answer, of course, but what happened is that technology is able now to detect cancer with more precision, and we have this technology helping. So that's why the number of cancer incidents increase. It's just the number of detection is increasing. And the cell phone users is the same. Technology improved, made cell phones more accessible to the population. But could be both, right? Who knows? So this is the lesson here, right? So it doesn't matter what you observe as a correlation or what our predictive model tell you, it's hard to guess what's happening underlying in the reality. So AI can predict everything, but that's the question. Does it explain the world? And because of this story, you probably are going to say no. However, what are the challenges? Why this doesn't happen? So challenges emerge because of biases and understanding this underlying mechanism. So we don't understand, first of all, many times that we predict a model, we use these very complex models, these black box models. So explaining the model itself is hard. But that is a step further that we want to know here, is explaining the mechanisms or we call it data generating process, is the model that actually generated the data, which is more like explaining the reality. So this is a good question. So we want also to provide unbiased estimate, right? So the case of the positive correlation, the model is going to predict pretty well that's a positive correlation for the example of the nurses and the mortality rate. But because if we don't have the variables explaining the size of the hospital, severity of the disease, and so on. So we want to provide unbiased estimates, and confounding or latent confounding is a big problem. So another challenge comes when you want to optimize or personalize approach. Again, it's the same issues of the biases. When you want to design a fair system, a decision system, because again, you need to understand how are the mechanisms, the underlying mechanisms of the model to know if this is according to our standards. We want to generalize well for different environments. So sometimes you are using variables that are very specific for one particular data set or one particular population, and you want to generalize or extrapolate to other populations. So it's important to understand the role of every variables in the model. So what can be done to overcome these challenges? So it's now touching the topic of interpretability, explainability. Maybe you've been working with that. So what people are doing right now in terms of explaining, that's a good question. Explaining what? But yeah, what do you think the field is doing for explainability? Who can give me an example, a technique, something that reasoning in terms of what? And what exactly do you think it's happening there? You are explaining what there? It's how the model is producing the output? Or it's explaining the world? Yeah, I think the field is now using a lot of these techniques for explaining the model. And what we need is actually understand the causal, the real world insights. So can model explainability provide causal insights? So why this is important? So we have like a lot of promises for model explainability. We have like in feature importance, sharp line, visualization techniques, something that people call it counterfactual explanations, but it's counterfactuals for the model. It's not for reality. This is really important to understand. Probing, you can try to understand what are the different outputs of a model, But what you are doing there, you're just explaining a model. Are you actually explaining the reality? And why this doesn't work? So why doesn't model explainability imply causality? So going back to the example of the nurses is really simple, but let's try to go into details here. So you got a data set, and then you got your best model ever, can be a transformer, can be whatever, that you did your best, and you estimated pretty well the probability of y given x, okay? Which was the first slide I gave you. And in this case, x is a predictor for y. So we will have a model where x is here. So you suppose that I model the problem, the data, and I fit this model. So I have this model here. This was the one that was fit to the data because I imposed that x is coming as an input and the y is an output. It's going to be in that direction. And yeah, that's it. And however, the problem is that there are many models. By changing the parameters of this model, which is again agreeing with x being the input and the y being the output, that can explain perfectly. There is a problem of equivalence here. So there's no identifiability of model. So there are multiple models that follow the same structure and they produce the same metric, let's call it, but it's actually, you could have the perfect model that perfectly recovers the probability of y given x, and they are still equally correct because they are explaining this probability here. The problem is even harder because you can actually have different models that again produce exactly the same probability of y given x, but they flip. They can, if you started, for example, with y being the predictor and x being the outcome, you would be able to produce this because this is as asymmetric quantities, a correlation. So you would be able to fit a model here. If you, instead of doing that, you could have like some latent confounding that you are estimating this latent. You could also produce multiple models that could answer perfectly, 100% accuracy for you because you have this quantity perfectly estimated. And it turns out that in our example, suppose this is the true model, right? The example that we were talking about the nurses, we said, okay, maybe there are confounders and the direction is even correct. But is the correlation or the model predicting the right effect? No, because I mean, if I don't have the latent variables there, it's not able to guess what was happening there. It's going to produce what the probability of y given x correctly, but this doesn't mean that it doesn't explain the real effect, the real causal effect, or the unbiased effect. And if you start explaining the model, you can do your best, and you can use all these techniques I told you, you are going to correctly estimate that sending fewer firefighters is going to help reduce the size of fire, hiring more nurses, you increase the likelihood of patient mortality, having cancer increases there. You're going to have exactly those answers because this is what the model is telling you, but this is not connected to the reality by the fact that you fit the wrong model. And what's the chance of fitting the right model here? This class is huge. It's really huge. I think this is a question to answer. Anyways, so how people know if it's a causal effect now? So going back there 200 years ago with Fisher, people discover randomized experiments, right? So you can basically access if X is actually a cause of Y by randomization. So if you randomize, you have two groups, you randomize the assignment of a variable X. So you don't know. So you want to know first if X is a cause of Y and can have or cannot have some confounding relationship. And then you randomize the assignment of the variable X in one group, you randomize the assignment of the variable Y X in another group. So you have two levels, supposed to a treatment, I have a placebo and a new drug. And but this this assignment for these groups is completely randomized, which means that there's no function, there's no, this confounding relationship is going to be minimized because since the assignment is randomized, there's no variable directly affecting my assignment or the value of the variable X. which doesn't happen in observational studies. Sometimes we see that a person is very sick and we give one type of medication for this person, or the person has a particular age or some other conditions. So the doctor actually takes all these variables into account to assign a treatment to a patient. And because of that, those are creating confounding we are confounding the relationship. But in a randomized experiment, we try to minimize this confounding. And if we just compare now, if the probability or the expectation of Y in the first group is different than the expectation in the second group, it's actually because after, so the only difference between the two groups has to be due to this assignment. The only difference between the groups is due to the assignment. That's why it's really important to be a perfect randomized control trial, right? If you have like biases in how you divide these groups, you can no longer have a causal effect, estimate your causal effect. And this is the quantity we most of the times we are interested. Like if you have like a discrete binary variables, it's just the difference. But you may have a continuous variable and just you want to understand this probability after having an intervention on the variable X. But how then we move from prediction to true understanding of reality without randomizing experiments? Because this is too expensive, we would have to do this for all possible variables that we are interested in. This is really, sometimes it's unethical in the case of the cancer, right? You cannot just randomly decide to give, like, make a person to smoke, to give some radioactive component to another person. You cannot do that, right? How can we actually detect if something is causing our variable of interest? So this started in econometrics already more than 50 years ago. Where Donat Rubin started the potential outcome framework. So maybe some of you have heard, if you are from economics, you probably heard about it. And after a few years, Imbens and also Yosha Engrist, they started, they created, for example, the theory of instrumental variables. They actually advanced a lot the theory of potential outcome. But this was always too hard. Like they use some assumptions, and it's unclear how this is connected. But they had so they had like their contributions because they started they defined the quantities, they formalized the theory. So they even won the Nobel Prizes in 2021 because of these contributions. It's a very long field. That's what I want to explain by history, that this doesn't started like 10 years ago. It's very long. But Perot he modernized the view, right? So the contribution of Perot, I would say, is that it created the theory of graphical models to make these assumptions behind even the potential outcome framework. What are the assumptions behind the methods that tries to infer causality in a graphical model, right? And he has this book, Causality book. During this lecture, I'm going to use his theory, so I'm probably talk about many topics that started using, so it's rooted in the Perot's causal framework. And he's currently the director of the Cognitive Systems Laboratory at UCLA. He also won a Turing Award because of his contributions in causality. And he has a book that's called The Book of Why, and there's a quote from the Book of Why. This is a very non-technical book, so everyone can, if you never heard about causality or what are the implications of the field, I really recommend you this book. You don't need any prerequisite to read it. And he is mentioning basically what I just mentioned in the first slides. Deep learning has instead given us machines with truly impressive abilities, but no intelligence, right? It's very good prediction models, but not intelligence. And the difference is profound and lies in the absence of a model of reality. So the reality here is the key for us. So the causality theory by Perot, as I told you, you can start by the Book of Why. There's like a very short book for people that also you can take as a course in statistics. You can read this in a few weeks if you're good. But it's very short. Like you can do like in a month maybe. It's very short. But the reference book is the Causality book. Of course, and the causal inference statistics, there is a website that I also recommend you if you're reading the book to access it and make the exercises there. But the theory became more and more popular, and people in machine learning and artificial intelligence getting more and more interested. So Joshua Bengio, for example, you all know him. He wrote this book by deep learning. He's a professor at the University of Montreal and also Mila. He also won a Turing Award for his contributions to deep neural networks, but he is really active in the field of causality as well, and he says that causality is the next step for progress in machine learning. And a lot of other books is now popping up. So, for example, there is this book by Jonas Peter and Dominic Jantzing and Bernhard Schukopf. Also, there's a new book by Elias Barenboim that he's still releasing the chapters, but there are a few chapters there. I really like these new lecture notes by Patrick Fouquet and Joris Muyai. It's a mathematical introduction to causality. It's very formal. I've been reading it constantly. This professor is from Carnegie Mellon. He's from statistics, but he's also formalizing the statistics, the perspective, some of the topics in causality. If you are more from like the machine learning perspective and potential outcome, I also like Brad Neal. He has like a very like simple ways to explain videos, to explain some contents. But anyways, the field is very extensive. You won't cover it. The first one, yeah. Elias, yes. When I was there, he started writing it. He's still doing it. Probably this size. Yeah, but I think everyone tries to put his perspective of the field, right? So when you read each of these books, you even feel that they are talking about different stuff. But it's because the field is very, I would say there's no unified way yet to, I think that's the hardest part of causality, is to have like a good guide to go through all the topics. And so like when I teach, I also have my own view, so I teach in my way. So anyways, it's still hard, but I recommend you to just go over all of it and maybe you grasp your own vision of it. Anyways, and as I told you, I will introduce you the PRO's causal framework, which is the same framework, right? So that is a unified way. So PRO actually, his intention was to unify the field, and he has this PRO causal hierarchy. This was mentioned in the Book of Why, and it basically discriminates the types of inference we can do. So the ladder, there are just 3 rungs, right? The first rung is the scene. And the first rung is interested in the probability of y given x. It's everything we are doing in AI, right? In machine learning. We are all here in the first ladder. Everything that you know about it is going to be here. This is even outdated. You should put all the methods here. This is a very big list. A list of methods to allow you to do prediction. So you can answer questions like, what if I see? Is this an example of the window? Like if I see the firefighters out there, if I have a symptom, what can I tell about my disease? If I cure my symptom, I won't cure my disease, right? It's like, it's just observation. Given the observations, I know how to guess the why. But the second rung is about this interventional distribution that I told you about, right? So that is now this intervention on the variable x. And it's the same, it's still a probability distribution. So we can have conditionals, we have like calculus and so. But there are different ways now to approach it. And reinforcement learning is one of them because you're doing experiments. So it's using experimental data there. Causal Bayesian networks is what we are going to see this lecture. And it's going to allow you, what if I do, or if I perform an intervention on X, what would be the value of Y, right? What would Y be if I intervene on X? My headache be cured if I take an aspirin. So there's an action if I take an aspirin. And the third layer is even harder, is the counterfactual. This is the real counterfactual, reality counterfactual, right? So if I observe a variable Y given a set of treatment X, but I want to change the treatment of this person, and this is more individualized inference. So I took an aspirin. Was it actually the aspirin that stopped my headache? So myself, I have a lot of other variables involved. Would be my headache stopped? I would still have the headache if I don't take the aspirin? You can ask this type of questions. And now you need more and more assumptions. It's not just the structure of the system. You would need to go to that level of the model, and identifiability of that model is really hard if it exists. And that's the goal, right? So the goal is like, how can you go from what you have, and sometimes what you have is just observations, from something higher in the ladder, so possibly in the second layer, which is the inference, the causal inference could be higher. And there is a theorem that says that the ladder almost never collapses, which means that you cannot expect understanding the full model of causality, the full data generating model, just using observations, because you cannot go to the third rung, which has the full explainability, to just data from the first rung. You can have partial understanding, and this is what we are going to do, but full explainability, it's almost never possible. Right? We will need like experiments lives in the second rung. So maybe like combining experimental data with reinforcement learning is, in my opinion, is a very it's maybe the way to go to reduce the size of the class of possible models that feature data, but it's still really hard to know if that's my real model, right? All right, so causality here is a key to overcoming AI greatest challenge. It's a very big sentence here, but it is true, right? Not that I'm saying that the causality field is done, but it's one of the keys, I would say, right? Why? Because it's very, it's formalizing from the beginning. So it's formalizing what you have, for example, data. So this is called data fusion. Sometimes we call it causal modeling. And if you have, for example, data coming from multiple designs of experiments, sometimes you have interventional data, sometimes you have observational data, sometimes you have from different populations. How can you put this together with that knowledge in a language? And this is the graphical language. How can you put that and use this as part of your inference framework? And topics are coming up in this topic. For example, causal representation learning is one of them, because sometimes you don't even know the variables that are important. So you have to learn the variables and then learn the model. Causal abstraction, something you don't want to have like an understanding, a low level perspective of a model. You want to go higher and see how the causal effects are. So you want to preserve the causal effects, but in a higher point of view. The second one is actually explainability, and here I say explainability of reality, right? So real explainability. We want to have a better understanding the true underlying mechanisms, and causal discovery is doing that. The third one is optimal decision making. So you want to know what's the best decision that you can do. This requires now understanding what are the effects, the causal effects in an unbiased way, and then gets the treatment that gives you the optimal outcome. So it's going to touch the topics of causal effect identification and estimation. Personalized inferences. Sometimes people define personalized inferences as conditional inferences. Like you conditioning several characteristics of a patient to the point that you can call it, it's more personalized. But the real personalized would be the individual level. And this is what the counterfactual reasoning is touching in causality. And fairness is, again, a way of explaining. So I would say it's an example of explainability, but usually it tries to incorporate counterfactual reasoning for understanding these mechanisms. And the last one is generalizability. So it's not only like a blindly estimation to get to predict if you will have like a good out of distribution performance. No, it's actually putting in the modeling all the assumptions to ensure that something that you estimate in one population is going to extrapolate to another population. This can be environments, can be from rats to humans. So the assumptions to actually work are sometimes strong, but you want to know what are these assumptions. So you model this. Questions to this overview? No? Now I'm going a little bit more to the details. Is a bit technical, but I hope you keep with me. It's not too technical. Yeah, if you have no questions, maybe I continue. So as I mentioned, there is a model, a data generating model, a model of reality. We call this model, we name it as a structure causal model, or SCM. So if you had it, you would have full explainability. There's no causality, it's just estimation of a model and done. Right? But what is this model? This model is just a tuple. You have like these 4 components here. We usually call V as the set of variables that we observe. So you have your data set. Those are the columns of your data set. That's it. There are, of course, other variables important to explain the world, right? It's not only those that you observed. So in the example of the nurses, we would have like the size of the hospital, the severity of the disease, and so if you don't observe, they're going to name as U variables, the exogenous variables. We believe that they follow certain functions. These functions are not deterministic. You have stochastics because these U's here are all random variables. So, but exists a function that takes as input the cause. We call it parents because we use these kinship relationships, and any other variables that maybe exist. Can be just a random variable, no informative, right? And the PA are the endogenous parents and the U's are the exogenous. So we just separate, but they are the causes. And we also, to fully specify the model, we need the probability distribution of these variables used. And one assumption that it's been changing, but most of the theory that I'm going to talk here, they made the assumption that the model is recursive, which is also translated to you don't have a loop. So it's the example that he was mentioning, what happened, like you have like the fire, then you have a firefighter, and then the firefighter change the size of the fire. This can be seen as a loop. Here we believe that we will have at least a good resolution. So if you believe that your data has some temporal effect, you would need to collect temporal data to actually disattach these effects. But people are actually, Mui, for example, the guy that I told you that I really like the lecture notes, he's working a lot on extending to cyclic mechanisms. And so if you have the SCM, so we call it observational or SCM, yeah, sure. The what? Okay, so we use this notation where these are the random variables, those are the values of the real values. Is that a question? Yeah. So PA is short for parents. And when I have like a big P here is because I'm talking about the variable. And when it's a small p, it's the value of the variable. But this notation is usually like a function of, so a function receives the values. So that's why they're small. But sometimes when you have probability, like this probability, what's the probability of U? If it's like a discrete variable, you would have what's the probability of having U equals to U. This is a short notation. More questions regarding to notation? All right. So as I was telling you, so that this structure causal model defines all these functions. And let's go back to this example of the firefighter. So here or I don't think that's the example of the variable. But anyways, let's assume we have two variables. X is a function of two u's now, so I don't observe the u's, and the y is a function of x. And I have a shared variable here, the uxy. If I just get the induced probability distribution of this model, I will get the joint probability distribution of over all variables that you observe. You can compute that or estimate that from data, but you have like the true probability distribution is just the induced from the model. But if you have this difference, right? So this is definition of correlation. As long as x is correlated to y, we will see that the probability of y is probability of y given x is different than the probability of y. And this is just a matter of correlation. And correlation can usually come from two things, either because there is actually a functional relationship, so one is the argument of the other, or because you have shared parameters. So even if I don't have this x here, x and y would be correlated because I have shared parameters. So there are just two reasons for two variables be correlated. And when we move to this post-interventional or just interventional model, what we are doing here is manipulating the equations so that, for example, I want to know what's the probability of y given an intervention on x. So I manipulate this equation for x, and I then estimate, or I see the induced probability distribution from that manipulated model. And in that example, we are going to name it, this distribution, as interventional distribution, and we will see that the probability of y in the interventional model, in the manipulated model, is the same as the probability of y of the pre-interventional model, because the equation of y didn't change, right? So I'm manipulating x here, but if you just get the probability of y, the probability of x, and you have to do this for all possible values of x, right? So this is for all x. But if you have one x such that this is different, then this is a cause. And this is the case where we have x as a cause. In this example, it's a cause. So because we have x here, x and y are still correlated in the induced probability distribution of the manipulated model. And we will see that for at least one value of x, we will see that the probability of y changes. Did I explain? I think it was confusing because I was explaining the case where you don't have the x first. So there are two cases. If I don't have the x, imagine that I just have the u's. And if I manipulate the equation, I would not have the x here. And then the probability of y would be the same as the probability of y in this size, if I don't have the x. But if I have the x, you change the equation of x, and you still change the equation here. So you see that these two are different, because this is set and he's not set. So you can detect correlations in the interventional distribution. If these correlations exist, then it's because of causes. Is the same reasoning of experimental randomized experiment, because the only reason of a variable y changing is because of this x. You eliminate the u's. If it's confusing, I'll repeat again.
What happens if like your x has like an effect on like a secondary variable, and then the secondary variable actually affects y? You could say it's causing that, but just imagine it's like something like, I don't know, I changed the number of nurses, so the hospital has more money, so blah, 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 so something changes here. There's like a very long chain of like causation, and you could say, well, yes, x is like causing a change here, but actually like there's so many things in between that it's
you still see the difference, because there is a functional relationship that's connecting all. So this is going to be an indirect cause. So once you change here, if you're not conditioning on any variable here, you will still see a change.
like, can you measure like degrees of causality, sort of like, because like
Exactly this
like super causal of this thing, you know, because there's 1,000 other things.
Yes, this is something that we call in the field as mediation analysis. You can see if but there's always a level of abstraction in your modeling. You're never in the resolution of atoms, right? There's always some reactions that you never observe, and that every edge in your graph or every functional relationship of your model is in some sort of abstraction, right? And so when I say functional relationship, is because this is not necessarily exist like a very, very direct, is still functions of functions of functions of functions. And I'm just saying there is a functional relationship, can be long. But if you really want to know, I want to know what's the effect of that variable in that other variable. When I know that these are intermediate variables, you can do this. This is mediation analysis.
Thank you for the great talk so far. Just to kind of respond to what he's saying, this is more a comment rather than a question. So where I come from is more, we deal with more mechanistic modeling, and we use data-driven models to actually drive into more precise questions. And so to his point, yes, like there are many, many different variables, but the power of randomized controlled experiments is that it gives you insight on how far, like what direction you need to drive to get deeper into the questions to figure out what are the mechanisms that actually drive a specific disease or specific cause. So that's just to kind of provide.
I see. Yes. Yeah, sometimes you want to know what's the best variable to intervene to see the optimal outcome. And the funny thing is that the closest one is not necessarily the one that gives in continuous variables, this is happening, linear models, this happens. But you can design like a discrete model where this is not happening. Sometimes a very far variable would affect more your outcome than the closest one in a graph. More questions? All right. So yeah, so if you think back there in statistics, so how many of you have heard about structure equation modeling? Yeah, so people from statistics already heard about it. And some people even call it confirmatory analysis, very funny. Yeah, but what is this? It's just that you came up with a model. It's a model, it's like a simplified deep neural network. It's just still a model that you came up with equations. And at the end, you estimate the parameters, and it is still valid if you are just trying to model correlation, so to prediction, or if you are correct about the equations, if you really have the knowledge to create the functions, yeah, you can call the coefficients as causal effects because you're modeling the structure causal modeling. Right? You're parameterizing the directions, you are actually writing the equations of the structure causal model. And here I'm even imposing linearity, I'm imposing normal distribution for the error terms. I'm telling you that all the error terms are all independent of each other, which in the field of causality, this is usually known as causal sufficiency. It means that the correlation between all the variables here, they are fully explained by the variables that I observed. So the error terms cannot be correlated due to other variables that I don't observe. So all of this started in statistics, and it's an attempt to specify the model that maybe is generating your data, but to actually call this confirmatory or to actually say this is a true causal model, it's a strong assumption, right? You really have to be sure that these equations are correct, the distributions are correct, and so on. So that's the lesson from here. The structure causal model is an encoder of functional knowledge. So you really need to parameterize all the equations. And this knowledge is usually not available in practice. So is it possible, that's the big question, is it possible to identify effects of intervention, so causal effects, from observational data, but without fully specifying this structure causal model, even in a no-parametric way, right? It's a big question. And the field actually tells us that, gives you conditions for that to happen. So this is the goal of the field. What are those conditions to allow you to estimate the causal effect? For example, if you have structure knowledge or the graph, you already have a way to specify just a qualitative specification. So you're not going to the functional level, but if you had, for example, no latent confounding, you have a way to estimate all causal effects already. Latent confounding is a thing that exists, so you will see that sometimes you have a way to identify the effect, sometimes you don't have, and this is what the field is about. So what is causal Bayesian network? So causal Bayesian network is now a graph. Do you remember the slides that I had the data, then all the graphs, and then all the modules? So we are now in the second column of the graphs. And it's representing a class of functional modules. And we call it DAG because the field started without modeling latent confounding. But when you put the DAG together with the latent confounder, sometimes people call this ADMG, a cyclic directed mixed graph, but it's a DAG with latent variables. I think that's the best way to name it. And the point here is that we are just focused on the structural knowledge, no functional knowledge. So we want to model the structural causal and confounding relationships of an SCM. So imagine that I'm not even writing the functions here. So that is the SCM, and it's in gray because I don't observe. This is the way that I write. And to derive the causal diagram for that structural causal model, I follow two rules. One is that every time that a variable, so I'm going to create a graph where a variable points to another. This is an edge in the graph. If this variable vi appears as an argument of the function of the variable vj. So basically here, let's go to the example. I have variable a is just a function of u variables. So u variables I don't even put here. So I don't note. So this is just for v's. V's are the set of variables that are observed. So a is a function of just u's, so there's no variable pointing to it. B is a function of a, and d is some u's, but then b is going to have an edge from d and from a. And c is a function from b and some other u's, so c is a function only of b. And the second part is now about the u's. So the u's are usually hidden. So as I told you, you don't even need to put the adds there, but they are there. It's just hidden. And if I was following the first rule, I would add all the u's as every time that they are arguments, I would put here. But the only ones that are relevant for the analysis, that's why we hide them, is those that create confounding. And confounding is when the latent variable is a common cause of two variables or more. So this is important to model. So if we have this, for example, if we are going to add this bidirected edge, every time if we find two u's that are correlated or if these u's are shared in the functions. So in this example, they are shared. UCD is shared for the function of D and C. So this would be like this, and then we just put the bidirected edge between them. And all the others that are not following this, creating this confounding, we just hide them, right? It's just a vision of a model that's encoding structural knowledge. And so what are the challenges of this perspective now? Dimensionality. Usually I don't have just three variables, right? So this becomes very hard to specify and has like a combinatorial explosion. Sometimes my knowledge is limited. I have a knowledge that allows to do some of the adds, but not all. And sometimes it's even inconsistent. So there's no agreement in the literature if it's from A to B or B to A. So that's a problem in Prezi. Sometimes there is a mismatch. The variables that I observe are not the variables that I'm interested. So for example, in images, the variables observed are pixels. And I want to know how I want to model the image as a whole, or maybe some parts of the image. So this image, the variables of an image are not even known. So we would have to learn them, or maybe combine pixels or combine variables to create a variable. So sometimes there's a mismatch, or like sometimes it's very high dimensional. I work with a lot of genetic data. I don't want to know if a gene causes another. Sometimes I want to know if there's like a regulatory, a pathway, a gene pathway that affects the other. I want to have a more abstract vision of the system. And the point is that the variables itself are not there, and you need to know them.
Excuse me,
Sorry.
I apologize. You may have said this already, but if you go back to the previous slide, the multi-confounding factors, Is there a methodology for identifying them? And if you've covered it already, I apologize.
What? Most confounding factor?
Yeah, the ones that you don't hide.
The ones that I don't have, they use?
Yes.
So, no, so this is just a graphical notation of a model. So there's no methodology. So you need to know from your head how, if A is a function of, if B is a function of A, and if you know that, for example, the example of the firefighters, I know that the fire determining the number of fires. So I put the edge. I don't know what's the function, but I would put the edge there. I don't need to know, I don't need to quantify it. I just need to know that exists a variable and it's influencing both. It's a qualitative description. I'm not asking you the function. I'm not asking the distribution. I'm not asking you the values. Yeah, you would have to have the knowledge. So for example, the example of the nurses. The example of the nurses, I know that there's the severity of the disease. I know that there's a lot of other variables that affect the hiring process, and they are going to be the U. I just need to know, put the variable there. This is all I'm asking. But this knowledge is already hard to have. Because if you want to be conservative, you say there's everywhere. There's latent variable everywhere. And if you are in this scenario, nothing is identifiable. So you have no way to estimate causal effects. So removing ads in this graph is where the knowledge is. I want to say there's no confounding here, and this is pretty strong. Right? And that's the challenge, right? So specifying the graph is hard because it's coming from knowledge. And the knowledge sometimes doesn't exist, there's no consensus, and there's mismatch. Sometimes the A variable is not the A variable that you're interested. It's like, how can I make up the... And so that's why it's coming. So causal modeling is still a very active research. And now it's in the name of causal abstraction, causal representation learning. And it's basically for the third bullet here, this is the part of learning the variables. And we will see a bit after in the lecture how you would learn this graph if you have just data, or maybe a combination of data and partial knowledge. A question there?
Sorry, I just wanted to know, how do you like go from a place where, okay, these events are correlated to knowing for certain that they are like, they happen 100% of the time? Because I think that's the real challenge in like trying to infer causality.
Yes. No.
And maybe like, I don't know, maybe we could make, in another alternative, we could make more like out of correlation. But yeah, how do you go from events having a certain probability than being certain? And I think a good example is like genetics. Like how do you like infer that someone is going to have a certain disease based on the prior history of genetic data, I guess?
Yeah, I mean, there are many challenges, but this is what I do. And you see, hopefully by the end of the lecture, I will go faster. Yes, we will see that. I like to take this more fundamental approach because it's how the field started. And to be honest, 99% of the community is still here. And I really like to know, because sometimes you are going to leave this room and you're going to search Google, what is causality? And people are going to basically have that for you. And this is not it's not the state of the art, but yeah, people are still, there are challenges here, right? So there's sometimes, you know the graph, but how you estimate correctly the probability of y given to x. This is a very active field. So they're very challenged, even if you have that. For abstraction, unfortunately, there's no way to learn a graph over latent variables unless you put causal sufficiency. I cite a paper that I just submitted, but people are usually assuming you have a graph. Most of the causal abstraction field is like you assume, even some works assume you have a model. It's even harder. So it's very fundamental, but we will have a way to do the completely data-driven way. All right, I'll go faster now. So causal representation learning, as I told you, is a very big field. Maybe I think I still have time. So one thing that allows you to model that is, suppose that you have partial knowledge, is something that we call clustered causal diagrams, or CDAGs. And imagine that I have a few variables or a bunch of variables, and for the relationship among some are unknown, but between others, I know it. So a strategy that you can do is just cluster. So you basically make a partition of your variables, and you try to understand how the variables between the variables inside of each clusters are related to each other. And the procedure is really simple. So suppose that it is the same way that we create the causal diagram, but now you have to look at if inside of the cluster that is at least one variable that's causing the other in the sense of having a directed edge there. If one pair is found, then you have to connect the entire cluster. So for example, here, if the cluster, and the cluster can be only one variable, so this reduced to the usual causal diagram, right? So maybe I know that X causes S causes Y, but I don't know the relationships between those variables, but I know that some of those variables causes X and some of those variables causes Y. And then I have this partial understanding. So a lot of people are now under this specification. And the confounding is the same. If you have at least one variable there that gets confounded with, I don't know, X, you have to put the bidirected there. And the same for Y. And the fact that I don't have a bidirected here is a very strong assumption that says no variable there is correlated, is confounded by a latent variable with S. Okay? And what this means is just is like enlarging the class of models. So a causal diagram is already a class of functional models. Now we are allowing a class of causal diagrams, right? So if I have that, I could, basically I'm just allowing for the possibility of having any type of causal diagram where you change the edges between the variables, right? So usually we have to now think this as equivalence class, right? I have to account for only the knowledge that I have, which is described here. And note that if you have all knowledge, you would go up, you would go back to the causal diagram. And if you have all knowledge, and if you have no knowledge, you don't specify. It's basically you are back to zero here. So, but sometimes you have knowledge for that, and these clusters can be created as much like in any way you want. It can be due to lack of knowledge. Sometimes you have no consensus, or like it's just because you want to have that level of abstraction. So this is a macro view of a system. And so clusters here are sometimes called macro variables, and it's just a coarser view of the SCM. Anyways, but that's the question that someone asked. What if domain knowledge doesn't allow you to even construct a cluster causal diagram? So I'm not going to learning yet. So this is after the break, according to my plans. But you really need to know that a causal diagram is not only a specification of causal directions and confounding directions. So for that, I need to explain what's Bayesian network. So who here have learned about Bayesian networks? Okay, so I go fast. Okay, so we go to the interesting part fast. So Bayesian network is just an encoder. So now it's not committed to encode causal directions and confounding directions. So it's just a graph that's committed to represent the joint distribution by representing the conditional dependencies and independencies. So you learned Bayesian network as that, or you learned as just Bayesian network learning? Who knows that the Bayesian network is a condition dependence map? Okay, just a few hands. But yeah, let's continue. So Bayesian networks are basically, you have, if you are under the condition that there's no latent confounding, we call it that we have the Markov condition. And in that, it holds that every variable is independent of the non-descendants given the parents. So here we use the notation of kinship relationships. But that's just a way to represent, so everyone knows, right? So if you have a joint distribution, you use the chain rule, you can factorize it by any topological order that you decide to choose. And by using dependencies that you know that exists in this distribution, you can simplify it. And for example, this you can remove some of the variables after the bar, and the ones that are left are going to be called real parents. And you have to be careful here that parents are not causes, are just parents of that graphical model. But you are representing a joint distribution in a simplified way through a graphical model. That's the goal. And if we call that P satisfies the Markov condition, if with respect to a graph, if you draw a graph, and this can be any graph, that is going to satisfy this relationship here. So for example, so remember, EDS has no causal semantics, so don't read EDS as causal here. But you can factorize V, the joint distribution, by the chain rule, and then you simplify each term here by some dependencies that you have in the distribution. And at the end, everything that's after the conditioning bar are going to have an edge. So for example, W here has just Z after the conditioning bar, so that's why there's only an edge from Z to W. Z has X and Y, so there are edges from X and Y, and that's all. And this actually represents, right? So you eliminate, so Y is independent of X, Y, and A given Z. So you eliminate these variables because they are independent. So you actually apply these independencies and you end up with the graph here. When you are, okay, questions to this point? Okay, so when you are in the semi-Markovian condition, this maybe you have not heard about it. So you can extend Bayesian networks to the case where you have latent confounding. But it's the same thing because it's just a network that you would have the use there if you are not hiding them. So everything follows. It's just that now we want to define in a different way so you don't reconstruct the use. It's a bit silly, but that exists is the same notion, is a generalization of the same condition. So now the variables are independent of the non-descendants, but now we call it extended parents. And the idea is still to represent the joint distribution in a simplified way. So you would apply the chain rule and so, but now after eliminate, so you would only remove the variables, and the variables that are left after the condition bar are not only edge that variables that are connected by a directed edge, but they could be just connected by a bidirected edge. And we call the ones left here, they are going to be called extended parents. This is a very, I would say this is just a curiosity. You don't need to know this terminology, to be honest, but I'd like to bring this because people think as Bayesian networks as a graph that has only directed edges, but no, if you are working with causality, if you draw a graph, that graph can have bidirected edges in the sense that they represent latent confounding, and the graph can be just being a condition dependence map. We're representing conditional dependencies and dependencies in your data. Yeah.
Well, to be honest, I got super lost here, so I didn't understand any of this part, but like, you think this is not important, right? Like,
it's not important. I just wanted to know that because we call it before causal Bayesian networks, and I want to connect here with Bayesian networks. Bayesian networks, probably all of you just learned the ones that have just a DEG, is only directed edges. But that is a generalized definition for Bayesian networks, which includes these bidirected edges. And the idea is exactly the same. So that's why you don't really need to know the definition. I can explain. The definition is like an extended parent is of a variable, any variable you have here, it can be just the parent itself, but it's the unit. Let's take the E here. You have to take like a variable that's before in the topological order that you chose to create the graph. And a parent is including the parent of the variable that's before in the topological order. So for example, A is a parent of E in that graph because it's a parent of C, and C comes before in the topological order. Intuition, if you want an intuition of that, is basically the set of variables. I'm going to give you the intuition with this separation. That's important to have now, but if you want the intuition right now, it's like E is going to be dependent of A as a parent, because once you add C cannot be, so C and E are correlated. So you cannot do the factorization, you cannot remove C from after the conditioning bar, for sure. So C is there. So this means that you're conditioning on C, and after conditioning on C, you open this collider. So A is still correlated to E, And you can never remove A after the conditioning bar. You never have independence of E and A once you put C after the conditioning bar.
Sorry,
Yes.
I'll just repeat to be sure
Yeah.
So you mean like there's like this arrow that is like dotted between C and D.
Yes.
That means like there's like a compounding factor.
Yes.
Here. So like once I put in C, that means that I will also have like this compounding thing between A and E because C is in between that.
Yeah, like imagine that you start writing the factorization here. So you choose a topological order and you want to simplify it as most as possible. To simplify, you need to use independencies. And you see that the probability of E, let's say VI is E, okay? Then you put all the variables after the conditioning bar first. You cannot remove D from there, you cannot remove E from there because they are neighbors. So you never have independence. So since they are after the conditioning bar, you have to ask yourself, can I remove A? And you see that no, you need to know the separation or at least induced independence. Why? Why not? Because if C and D are there, E and A, you would have to have probability of E. You would have to have probability of E given D and C and A different than probability of E and C and D. But this is never going to happen because once you have information of C, you have information of A. There is a collider here, so it's easy to detect that. So A is going to never be independent of E given C and D. So A is going to be in the term, so let's here. So A is part of the set of variables after the bar. And I cannot call it parents as the notion we had before, but it's dependent. And that's an important thing to know, which means that once you have a model, suppose I have a this is very connected to predictive model because it's correlation. So if I want to predict the value of A, D and C are direct connections, so they are for sure good predictors. But A is also going to be a good predictor, although it's completely far from the story here because it's correlated. So it's bringing information of C, right? So it's giving information of E. We will see it better later. I want to finish this, it's fast, so I go a bit faster now. So this creates a Markov equivalence class in the following sense. Suppose that I have probability of X and Y, and I observe that X is correlated to Y. And this is the reason why correlation between two variables in a non-parametric way is not going to automatically give you causation. Why? Because you start with one factorization. So you start, because I told you can get any topological order, and this process is going to work. So suppose that I start with Y first, so Y given X and X. And this creates, and then I could flip, I could start with another topological order, and I have a bit of X and Y given Y, X given Y and Y. So this two represents the joint distribution. It's because you can choose any topological order. And this creates two different probability, two different Bayesian networks where after the conditioning bar are the parents or the extended parents. So for example, I can draw this graph, I can draw this graph where X is pointing to Y. So all the extended parents point to Y. And in the Y case scenario here, so I have Y after the condition bar, I can create this one or I can create this one. And this is in both because it is extended parents for both directions. The point is that all these Bayesian networks represent this joint probability distribution where X is independent of Y. So this entire class of models are going to call Markov equivalence class because they are all Markov equivalent in the sense of being a condition dependence map. They are all working to represent the joint distribution probability of the joint distribution of X and Y. Okay, so from data, if I just have data, just have independencies and dependencies, I won't know what's the direction because I have this entire class of possibilities where the edges are flipping. But now, so our models imply no independencies and there's no invariance here. But I could go further and have, for example, this X, Y, and Z. And then and then the case where X is independent of Y given Z. This I observed. And if you start factorizing and following the rules where I put all the variables after the conditioning bias, adding the adds into the variable before the conditioning bias, draw many graphs. If I choose another topological order, I will also use this independence only to simplify, and then I can construct different models. And it's the same. And okay, it's again a case where I have a class of models. They are all independent, but there is a invariance now. The invariance, it's not very clear maybe, but the invariance here is that Z, the variable Z, never happens to have two arrowheads into it. It's either, if I have one arrowhead, then there is a tail. If I here, an arrowhead, then a tail, arrowhead and tail. Tail, arrowhead, tail, arrowhead. So the point is that it's always a non-collider. And there's always never, there's always a non-collider. And there's another case now. I suppose that I observe that X is independent of Y marginally, but all the other are dependencies. So I list all of those, and I can only apply this independence. This is the only independence that exists. So I start factorizing again, and the list of models now that I can construct, it's, again, they are all called Markov equivalent, but now it's a more clear invariance. And you see that all variables Z's, they have arrowheads into it. So it's a class that all models, they are explaining your joint probability distribution, but you can learn an invariance. And now it's starting from the question of the girl. She asked, can we learn something? And yes, this case is not very causal yet, but you learn that Z is not a cause of X and Y for sure, because there's never a tail out of them. Doesn't matter what's your true model, as long as this is agreeing with my joint probability distribution, because I have to trust something. So I'm trusting that I have data, that this data is representing my joint distribution, my joint probability distribution. And if I want to represent all models that are compatible with that data or with this set of conditional dependencies and dependencies, doesn't matter the model that I'm going to fit, this model is going to have Z as not a cause of X and Y. So I learn Z is not a cause of X, Z is not a cause of Y. This is the first principle, the first rule that we will have in causal discovery. And maybe we go to the cough break now, because now it starts. All right, I'm a bit behind, but I think I will go slowly anyways, because I think it's important for everyone to actually understand. But this is a question, so I think since many people of you already heard about the separation, Bayesian network, so probably heard about the separation, right? So who knows here, who here knows about the separation? No? So you learn Bayesian networks without. All right, that's good then. Then I go over the details. So this separation is now a tool that is going to do the reverse process we did before, right? So a Bayesian network is trying to represent a joint distribution through a graph. And the edges of the graph doesn't need to have meanings, as long as they have they factorize in a way that the variable given the parents or the extended parents are independent given the donor descendants. So this is a property. As long as this is fitting, that's fine. Now it's the reverse process. We want to see it, we will have a graph as the input, and I want to read what are the dependencies and independence that's encoded there. So it's a tool to read off from graphs what are the conditional dependencies and independencies implied by the graph. Okay. So for that, I like to start with some very basic graphs to build intuition. So suppose that I have, we call it fork because it's like, it's just one structure. It's very simple. It's just three variables, but people like to give names for structures of 3 variables. But anyways, let's call it this set of 3 variables. We have X, Z, and Y. And I give an example. X is supposed obesity, Z is age, and Y is baldness. Okay. Okay, everything is simplified. I'm not telling that this is the real model. If it's possible to have more variables or even like latent confounding, but it's an example. If I see X and Y here, so I see people that are obese and I see people that are bald or not, so I have 2 columns in my data set, and I see a correlation. Okay, there. Why you think that is a correlation? I mean, my example is mostly because of age, right? So when you get older, you are not say deterministic risk. So in probability, it's like there is an increase in probability to be obese, and at the same time, you get baldness for men. It's missing here the part of men. So anyways, but as long as you take into account the age, you see that these 2 variables are not dependent anymore, right? You see that you take young people, they are not even bald, right? Or like, but you see that the correlation between both are explained. And this is then a triple, right? A graph of 3 variables that is encoding the fact that X is dependent of Y, but X is independent of Y given Z. Then there is another graph that now it's a chain because the edges are going to one direction here. And it's an example where I have X as family history, Z is diabetes, Y is stroke. And so, okay, diabetes causes stroke in my example, or I'm using here notion of causality already because it doesn't matter here. But Z is, in my example, causing stroke. But suppose that I don't have the variable Z here. The person doesn't, I don't know, I don't have a test yet for the person to have diabetes or not. But I know that in her family, there are a lot of story, she has a lot of history of diabetes in her family. So the probability for her to increase to have diabetes is going to be higher, and this means that the probability of Y for her is also the probability to have a stroke so to be also higher. So this means that X is dependent of Y as well. But now suppose that I say that the person doesn't have diabetes. So it doesn't matter now if she has the history of diabetes. Once I know that she doesn't have diabetes, she won't have this stroke. Because in my example, there's no directed edge from here to here. It's very simplified, but that's the point. And so it's another example, another graph, which because they are Markov equivalent, right? That is also explaining that X is dependent of Y and X is independent of Y given Z. But we can have another structure. We call it, without the W here, it's called V structure because it looks like a V. But it's a structure where Z is a collider, and now X and Y are causes of Z. And this example is the example where X and Y are, X is diet, Y is physical activity, and Z is the obesity. And I want to explain here the intuition. Suppose that, so diet and physical activity, in my example, not always is like that, they are independent, okay? So people can have a good diet and do or not exercises, and this is independent. In reality, this is not happening, but anyways. Then suppose that, so this is independence, they are independent. So X and Y are independent marginally here. But suppose that I observe that the person is obese and at the same time, she's doing a lot of exercise. Can you say something about her diet? She's doing a lot of can you say it's a poor diet or a very healthy diet? What do you guess? Poor diet, right? So the 2 variables that were independent, because we have information of a common cause, a common effect, sorry, we have information about Z, they become now dependent because Z has information from X and at the same time it has information of Y. So once I have information about Z, I can have that information of Y that is going to have correlation of X is going to be correlated with Y. So 2 variables that are independent, they are explained to be correlated once you condition on the variable in the middle only in this model where we have a collider. Remember the example we have that all models that have X independent of Y and also X dependent of Y given Z, they are always in the situation when Z is a collider. And this also is the case if we have a descendant of a collider, because it's, again, bringing information of the obesity. So X and Y is going to be dependent given W. It's the same example. Suppose the person has a heart disease and is doing a lot of exercise. Can you tell something about the diet? It's going to be poor diet because it's just a proxy, right? So the two variables that are independent here can be two variables that are independent can be dependent conditioning on the collider or in the descendant of a collider. And so how can I read those dependencies and independencies just by looking at the graph? So we need to understand triplets. So triplets, I started with triplets because they are fundamental. And there's two types of triplets. Either they are active or inactive. So we define as an inactive triplet. So three variables, I'm calling I, M, and J here. They are said to be inactive. It's always relative to a set Z. If the middle node, VM, is either a non-collider and the non-collider is in Z, so that's the example that is the chain, and I didn't put any bidirected edge there, but the point is that the W is not forming a collision, it's not a collider. As long as it's a non-collider, we will have a representation of two variables that are marginally dependent, but once you condition on the variable in the middle, they are to be independent. And here it's a graphical notion. So we are going to say that X and Y relative to a set Z that contains W is going to be inactive when we are talking relative to the set Z, right? So it's a graphical notion which is representing inactivity. And this just relies on if the variable in the middle is forming a non-collider, and the non-collider is in the set that I'm talking about. This other situation is the opposite. So it's inactive if it's a collider, but the collider is not on the set that we are talking about. It's like the conditioning thing, right? So if I have a triplet where W is a collider, it's by default is inactive because it's referring to an independence. But once the set contains the variable W, if the W, or if it contains the descendant of a collider, then it's not going to be inactive. So it's the second condition is like it's a collider, and neither the collider nor any of its descendants is in the set that we are talking about, right? So it's the opposite. So it's simple. And this separation is now a condition that now is a property between two variables that not necessarily are connected by just a triplet. So this separation is going to talk about paths, so long paths in the graph. And a path in a graph, this is a DMG, but it's any graph that we are going to talk here in this lecture, is said to be I don't like the way that's written here, but a path is not disseparated. So two variables that are connected by a path are called disseparated, or the path is called blocked. So the path is blocked, and the two variables that are connecting, so the first variable and the last variable of a path, they are disseparated by the set Z, if and only if P contains an inactive triplet. So the entire path are connecting two variables. So these two variables are going to be disseparated if at least one of the triplets in this path is inactive, because it's blocking the flow of information. That's it. And the path is going to be called blocked. So the set Z is going to disseparate. So now again, the set Z is separates X and Y if and only if Z blocks every path, because two variables can actually be connected through several paths in the graph. So the point is just, I want to know if information from one variable is arriving in another variable, right? And for that, I need to at least one of the paths to not be blocked. So if all paths are blocked, they are disseparated. And to have one path blocked, I just need one triplet to be inactive. So to have all paths blocked, I need at least one triplet in each of these paths to be inactive. Okay, so let's see examples. Maybe it's going to be clarified. So I have a bit larger path here, is longer, is two triplets. So X and Y is connected by only one path. And I want to ask if X and Y are disseparated by a set. Let's call the set here. Is X and Y disseparated by the empty set? So I just want to see if these two variables, Cx is, the information of X is arriving the information of Y. And for that, I just need that the path, the entire path is composed by triplets that are not inactive. Everything has to be open, right? Is this clear? So how a triplet is active or inactive? So to be active, you need a non-collider. So the non-collider allows the information to flow. So I have a non-collider here and I have a non-collider here. So if I'm not adding W and B to the set Z, it's the same as I'm not blocking the path. So it's free and the information from X arrives on Y. So it is disseparated? No, because there's flow of information. But if I now put B on the set Z, it's the same as conditioning on it. Then the first triplet is going to be inactive because non-colliders are inactive with respect to a set that contains the non-collider itself. So this triplet is going to be inactive. So the information that was in X arrives in B. I cannot go further. So it doesn't matter what's happening with the other triplets, it's not going to arrive there. So it's blocked. The entire path is blocked. So X is disseparated from Y given B. So it's check. What if it's W? What do you think? It's symmetric, right? So the information is going here. Well, it arrives in B. So B is not in the set. So it continues because it's a non-collider. But then it arrives on W. W, it's part of the set. So it's kind of conditioning on it. So the entire path is now blocked because I have W on the set. What if I have B and W together? Doesn't matter, right? It's just blocking more. Now, what if I have colliders? So I have X and Y connected by a triplet that by a path that has two triplets, and both of them have colliders. So the collider has the opposite effect in terms of dependencies and independence. So without conditioning on B or W or putting them in the set Z that I'm talking about, this is the first triplet is inactive and the second triplet is inactive. So if my set Z is the empty set, which is the natural way of observing the path here, then X arrives in B, but there is a collision, so information doesn't go, and doesn't matter what's happening after. It's just, you just need one inactive triplet, and that's it. So X is disseparated from Y, given the empty set. So yes. What if I condition on B? So conditioning on B, or putting B on the set, if B is a collider, it opens the collider. So conditioning on a collider opens the collider and makes X dependent of W. Is the case of the diet and physical activity. So once you have information on B, it's now connecting, making the information of X coming to W. So you open this triplet, but W is still not part of the set. So it's a barrier. so the information won't flow. So one triplet is inactive is enough to block the entire path. So X is disseparated from Y, even though I open this first triplet, because I have a second triplet that is inactive. Is that clear? All right. So yeah, W symmetric. What about both together? Now I put W and B, and both of them are in the set. What do you think? Who thinks is disseparated? Who thinks is not disseparated? Okay. Yeah, so you are opening the triplet. So if you condition on a collider, which means putting the collider on the set, you open the collider and you make the triplet active. And now this is active. Then you arrive in the second triplet, it's again active because W is also in the collider. So the information flows, right? So information of X is going to arrive on Y. Okay, so it's disseparate. It's not disseparate. What about this one? This is more complicated because if I look at how X and Y are connected, there are two paths. And to be disseparated, all paths needs to be blocked. So if you look at this path over one triplet, X, B, and Y, and another path that has two triplets, X, B, W, and Y. Okay, I need to block both at the same time, given one particular set. So what happened with the empty set? Is there a path that's entirely made of triplets that are active? Who thinks that there is? Yeah, okay. Which path is this? The directed one, exactly. So the flow of the information is flowing through this directed path here. So it doesn't matter what's happening with the other paths. I know that information is arriving, so it's not disseparate. What about now if I put B on the set? Then the first path that I had, it's going to have like a non-collider because XBW is a non-collider in this directed path. So if I block the first triplet, because I'm putting the non-collider on the set, this entire path, this directed path is now blocked. But this is not enough because I have two paths. What's happening with the second path when B is in the set? Now X, B, and Y is only one triplet where B is a collider. And since B is in the path, is in the set, then I'm opening that second path here. So it's arriving information. So it's not going to be disseparated. What about W? I block the first path. It's the same case as before, but it's hard to see here. But maybe some of you know what do you think is happening with the first path? Is blocked or not? Who thinks it's blocked? Who thinks that's not blocked? Okay. Why? Because you have a descendant of a collider, right? So this path X, B, Y is a path that is a collider, but W is a descendant of B. And since B is part of, since W is part of the set, this collider here opens. It's the case where we were observing the heart disease. So you open the collider. So it's not blocking the second path, so it's disseparated. And BW, I mean, is blocking these two, but anyways, it's opening the collider because you're directly putting the collider on the set Z. So it's also not. So this is a special path, a special structure is called inducing path. It's like it doesn't matter what you do with X and Y, although they are not connected directly, they are never going to be disseparated. And you will see this is a model that explains cases where X is never independent of Y. dependent regardless of the conditioning set. And that's the thing here. Yeah, sure.
Often does that show like in reality? Like this type of stuff.
I think can happen.
It's difficult, like looks like would be like problematic.
Yes, it's really problematic, but this has to be accounted for. That's why the theory, I'm bringing this type of things. You know that I told you, right? Graphs are always an abstraction, and bidirected edges are missing information. So you can get an example where it's a chain, and suppose that I have now a variable that affects B and affects Y, and I remove it from my set because it's latent, it's already creating inducing path. This happens, I mean, I cannot tell you this happens a lot in real world because we really don't know the real world. I mean, I can learn things, and when I learn, I have an edge. This is going to be always represented as a direct dependence because I could never found the independence, no matter I tried with my current data set. So I will always put these two variables direct connected in a graph if I was learning it. But this doesn't mean necessarily that there is a direct edge in the real model. It could be an inducing path. So edges are going to be just representations of inducing paths in the future, in the learning process. Anyways, but that's a tool, a very important tool that is mapping everything that's disseparated in the graph as something that's now a property of the probability distribution, which is independency. So we expect that if this graph is actually satisfying all dependencies or encoding all dependencies and dependencies that you want, we call it as faithful to the distribution, then every disseparation is going to be mapped to independencies, and at the same time, all dependencies, all deconnections, which are non-disseparations, are going to be implying dependencies in the probability distribution.
Yeah, so I have two questions. The first one is, I'm not really understanding the part where you control for more and more the mediator in the middle, the BW, and then suddenly it collapses. So you say it's open, so I don't know, what does that mean, open? And
Okay. I was trying to make an analogy here because we think about sometimes, because this path is just trying to represent like deconnections or like if two variables are connected, not necessarily there is a flow of information in the sense that what's known from X is going to like the probability of X is like in terms of probabilities, exactly the probability of X given Y is going to be different from the probability of X. So we usually try to, I mean, in a graph, we cannot just say, okay, if there is a path, there is a connection, they are dependent. This cannot be the case, right? To actually know if it is representing a dependence or independence, we need to use this separation. So when I say open, it's because in my mind, I thought about like a pipe, like a water pipe, and I want to know if the information from X is flowing and arriving on Y in the sense that now they are correlated or dependent. And when I say open, it's just because of that. It's like the pipes are open or the pipes are disrupted or something like that. I don't know, do I answer your question?
yeah, but then it opened another question where when we remove the latent variable that caused
That's what.
Yeah, I mean, also in the third case. Yeah. So when you say when we condition for B in the view, it basically let's say there's a third variable that caused both B in the view, right? It's latent, and we remove it. Basically, we create that dash arrow.
If you remove the edge, so if there was if it was the full path here would be X, B, U pointing to B, U pointing to W, and Y pointing to W. But the reasoning is still the same. Like if I want to see if X is independent of Y, I just need to check if this path that now has 5 variables is blocked or not. And since I have a first triplet, so marginally, like without conditioning on anything, the first triplet is inactive, we will have already the entire path blocked. We will have now 3 triplets, right? X, B, and U. This is going to be inactive. B, U, and W is active, but doesn't matter. And again, U, W, and Y is inactive. So it's a path with 2 inactive triplets. And so marginally, X and Y are still separated, which is going to imply that X is independent of Y in the distribution. So here you could, I mean, the fact that there's a bidirected edge is just a simpler way to represent
Like,
this.
question, if you condition on the U, does it change anything?
Yeah, if you had the U and you condition on U, it's still now the 3 triplets are inactive.
Hi. So first a comment, then a question. My comment is because I'm electrical engineer, when you say the path is open, for me it means that the circuit is open,
Yeah.
and therefore it's not actually connected. So
I know.
and the question is, I'm probably jumping ahead, but does it make this last one harder to infer because of you really don't have a way to block and just to like if you change on one side?
No, it doesn't make it harder. It's just that the characterization of the models have to now, every time that I have a dependence, I have to imagine that could be a model where the edge can be not only an edge, but can be an inducing path. So for example, you'll see further an example of this, but if I have X, B, W, and Y, I will see, so the graph that represents this model here is going to be a fully connected graph because nothing here is independent. No, wait, X is independent of W, given B, whatever. Yeah, so you see some independence, but X and Y are going to have a connection between them. But this edge means if I wanted to enumerate all possible graphs that's part of the class, I would have to have the one that has an edge and the one that has an inducing path. So the enumeration is more complicated, just that. All right, more questions? Okay, so yeah, so these separations correspond to condition independencies. And this is very interesting to connect now again with prediction, right? So suppose, I will skip this definition because it's not intuitive. I go directly to the intuition. Suppose that my goal is to predict the variable V, prediction, okay? Prediction, not causing. So the variables that help to prediction are those that are correlated. And of course, then you start with the set of neighbors. So if you were designing a model that has the best prediction for the variable V, it would definitely include the neighbors because they have correlations. However, once you add the neighbors, you are now conditioning on them because you have information of them. So you're bringing to the model the fact that you know the values of these variables. And now that you know the separation, you know that variables that are just connected by colliders are going to become dependent. So the best model for prediction are those that includes not only the neighbors, but we call it the parents of the children. When you don't have latent confounding, so you have no bidirected edges here, but it's intuition. The intuition is like once you add the neighbors, you may condition on colliders, and when you condition on colliders, you will start now creating a larger region of influence where these variables that have just a collider between them are now to be connected. So this variable is also going to be relevant for prediction. So if you were like, for example, getting the feature relevance of a random forest, I don't know, it can be this one. Doesn't matter because as long as it's associated, it's going to be part of your prediction. And this extends to the semi-Markovian case. So again, I don't go with the definition, you can check later, but the intuition is exactly the same. So every variable that's a neighbor Doesn't matter if it's a cause, if it's an effect, if it's just spuriously associated, which means just a bidirected edge. They are going to be part of it, of course, because they are correlated. But once you add them, you bring information of them. So you start opening this. Now that he said opens, I'm having a hard time. But yeah, you are like, you are activating the triplets. You are now activating this triplet and making this variable correlated to this one. So this is going to be also a significant variable for prediction. And this can be very, very long, like in this example here. So you add this one because it's a neighbor. So now this one becomes significantly associated. And because of that, there's also a collider here. This becomes a significantly associated. This can be very, very low. So the fact that the variable is a good predictor, like a really highly correlated variable, doesn't mean anything. That's the point. That's what I'm telling you, right? All right, so let's go to the point. It's a bit long introduction, but that's the question that everyone wants to make here, because we are machine learners. So can I learn a machine now? So can I learn this class that's called Markov equivalence class? And I don't want to do any randomized experiments. I'm just a data scientist here. I got a data set. It's completely passive collected. Can I learn it? And yes, so there's a big name here, but that's just a disclaimer. So you can learn, but if you don't want to make any assumptions regarding the type of model that you are there, or like the type of distributions of your variable, so in a completely non-parametric setting, and you just have observational data, okay, you are going to learn only up to the equivalence class. So you're going to learn only the invariances of all the models that are possible to explain your data set. And this is going to give you, it's going to explain the real world, because I'm not fitting any model here. I'm just saying, doesn't matter the model. If you were to fit a model, this model has to be part of the Markov equivalence class if it's correctly learning the joint probability distribution. And since it's an invariance, this is going to happen to that particular model. So there are two types of classes of algorithms that do that, either constraint-based or score-based. The constraint-based is based on condition dependencies tests. So you actually go pair by pair of variables, checking if those variables are dependent or independent of each other, given some other variables. And there are the score-based that tries to use a global score, a global fit, goodness of fit, to see if the model is good. And if you are in this field, I would say if you are working with causal discovery, you are going to see these two assumptions very, not assumptions, but you are going to see these two types of learning, I would say, that's called for causal sufficient systems, or for causal insufficient systems. But basically, it's assumption involved. So if you read that this algorithm only works under causal sufficiency, what is actually telling you is that I'm assuming that your data set has all variables necessary to explain confounding. So you have no bidirected edges in my graph. So it's Bayesian learning, Bayesian network learning. Maybe you have DAG learning. So most of those algorithms, they are going to assume causal sufficiency, right? So if you are in this context, you are fine with that. But there are other algorithms that are not going to assume that, and they are going to take into account latent confounding, and then it's going to have a problem of the inducing paths, and this becomes much more complicated, but there are algorithms for that. So the strategy for score-based, I told you, is a search, basically. Of course, it's not an exact search, although if you do exact search, you get a better, you have a provable way to say that you founded the true class of models. But usually it's a search, can be like a greedy search, or can be some optimization approach, but you have a score and you want to optimize, you want to find the graph that optimizes such a score. And under causal sufficiency, you have many. I think I have here, under causal sufficiency, you have many algorithms that score based. So those are just some references. I'm not going to be into this too much. But if you want to account latent confounding, you have also a bunch of them, but usually they assume some parametric some parametric form and some distributions. So most of them are working under the case that you have a linear Gaussian modus, because then you have a score for that, even if you have latent confounding. Like there's I won't be able to teach this here now, but now the causal diagram is going to be represented by a maximum ancestor graph. And that in the linear Gaussian case, you can find the class of mags instead of the class of causal diagrams, but they are equivalent, that maximizes that score, and this corresponds to the truth. Yeah, there are other algorithms, for example, we see NADMG that they even try to go to the level. I don't want to go, you ask me later this, but anyways, people are also trying to go to specify the structure. So the structures, for example, both free, or so you don't have like a bidirected edge for direct edges. Anyways, and then you can do something more. Anyways, but the constraint based is kind of, if you are in the setting of latent confounding, you want to not assume parametric assumptions, you go to the constraint based setting, because condition independence tests can be developed by all types of variables. And so that's why I'm going to present this now. So the strategy here is still to construct a causal discovery, but it's going to align to this entire set of dependencies and independencies that you observed in your data set. And you're going to observe this using a condition dependence test. Under causal sufficiency, again, this is started under like several years ago, but there's like IC algorithm, PC algorithm, and the idea is that they start learning first the skeleton of the graph, which are like if there is or not a way to make two pairs of variables independent. If there's no way, you keep the edge. And you basically perform all these independencies. And a good description of this algorithm is in these books by Peter Speartz and Clark Gilmore and Richard Shines. But I think I can explain this in a quick way. So in 1995, Speartz also generalized this algorithm, the PC algorithm, to account for latent confounding. It's called FCI. And Zhang in 2008, he proved that a specific set of rules are complete, in the sense that they are going to really learn everything that's possible to learn, or which means it's going to learn all the invariances across all these models if you have just observational data. So it's a very good algorithm. There are like many variants because of one particular assumption that it does, that your statistical tests are correct. So you're converting now the problem of causality to a statistical problem, but it is still like you need to make sure that your statistical tests are working. Otherwise, you're going to just put wrong dependencies and dependencies in your model. So there are several variants that makes it a little bit more robust. And there's also set-based algorithms. Set-based algorithms, they convert condition dependence tests into logical constraints. So a bunch of condition dependence tests together, they imply some relationships already. And something that happens because of the inducing paths is that we don't longer know if a causal relationship is a direct relationship, but we call now if there exists a path that goes from one variable to another, we call this as an ancestral relationship. So many times when we are in the context of algorithms that are learning under latent confounding, they are going to learn an ancestral graph instead of a causal graph, but it's the same thing. Is the fact that now instead of X directly causes Y. It's just that X has a path, a direct path, a causal path that goes from X and arrives at Y. But anyways, it's already an abstraction. So what is direct is a very good question. But many times here you listen to me, let's say ancestral relationship, but it's a causal relationship. And the set-based approach are also very interesting because they convert some condition dependence tests into constraints, and then you apply an algorithm that's very similar to the FCI. But the goal here is to learn a class of all models that are agreeing with all sets, with all dependencies and independencies that you observed, or the logical rules that you derived from the condition dependence test. That's why it's called constraint based, because the set of dependencies and dependencies, they create some constraints. You have to now find models that agree with everything. And because of these constraints, you rule out some possibilities, and then you learn invariances. So one of the algorithms, for example, that's a set-based is this ACI. It's ancestral causal inference, just because of what I told you. Anyways, but what's the idea of that? The idea is that, as I told you, you have data, and we don't know. We don't want to care about what are the models, because there are multiple models that could generate my data. And I don't want to specify, I don't want to assume distributions, I don't want to assume functional relationships. I want to use just data. So from data, what I can do is estimate, is identify through a condition dependence test, what's the relationships between the condition dependence relationships between every pair of variables given all possible conditioning sets. It's a really, really big set of dependencies and dependencies. And you do that, and if you were enumerating them, you would just create, as I explained before, in a way that you explain the joint probability distribution through these Bayesian networks, and you would create a Markov equivalence class. But the causal discovery algorithm does this for you. So it's going to and this is an example, for example, the FCI algorithm. This is going to learn all the invariances for you. And it's going to return an object that represents the class. And this object is called partial ancestral graph. Again, ancestral because of what I told you. And it's partial because sometimes you don't learn. It's a known invariance. And known invariances are going to be represented by circles. So this is the example of the collider that I explained. You see, the only invariance is that Z is a collider. They have arrowheads into it. But you could vary whatever. If I go back here, you see, oops, I go back. Here you see sometimes I have a tail, sometimes I have an arrowhead, so it's a known invariance. So that's why when I go to the representation, this is a circle. The point is just that the data allows you to have a model that either Z is a direct cause, X is a direct cause of Z, but could be also just confounded by a latent variable, right? So you have no ways, it's not a limitation of the algorithm, it's a limitation from the theory that says this data set can be explained by many models. All right, so this is a paper I really recommend you to read if you want to read about, because all the definitions that I mentioned, it's in this paper. So it's a bit hard, but if you go over every definition, you learn mostly of the definitions necessary for understanding at least the FCI. Yeah, so that's the point. So here, if I have a circle, I have no idea what is this, but if I have an arrowhead, I know that Z is a known ancestor of X, or Z is a known cause of X. And the same for Z is a known cause of Y. So what's the pipeline of the algorithm? So the pipeline, so this is the unknown reality, right? So it's in gray here. It's just for you to know if I'm going to get the right answer, but this is not part of the input of the algorithm. The algorithm starts with a complete graph. And then using condition dependence tests, you go and check all the independencies that are observed. And you assume that if there's, so you actually go by pair and test the conditioning sets. That is a strategy to go and not test all of them. I won't go through it. But the important part here is this assumption that's called faithfulness, that if you observe this independence is because it's really an independence implied by the module. And this is kind of problematic, but it's a statistical issue is no longer causal issue, right? Because this issue happens with everyone here. We have false positives, false negatives. So if you get more and more data, you explain more these statistical relationships. So it is okay-ish, but we will talk more about how people, even me, like how we are improving this situation here. But there is this assumption, so let's assume that you actually have these independencies in the true model. And if you had here the true graph, you would see through this separation what are those independencies implied by the model, and you see it's the same. I'm saying that's faithful. And once I see independencies, I remove the edges between the pair that's become independent, which means that this pair could have the dependence between this pair of variables was explained away, or like there is a condition dependence that made them independent. So I remove the edge. They're not directly connected. The edges that are left here, again, it can be an inducing path, it's just, or a direct edge, but the point is that they couldn't be made independent. But then there's a set of, it's actually 11 rules. There's the rule 0, which is finding the colliders, because the colliders are very special. But then there's like a lot of other rules that basically follows. The proofs are very easy. Like you have to make sure that the graph is acyclic, because we have a cyclicity assumption here, and you have to make sure that the results from the previous steps are correct. So you already found all the colliders. So basically the rules are really simple. So if you go to Tang paper, you easily read the proofs. And they are complete in the sense that once you apply one after the other, you have a graph like this one. And now you see a more interesting graph, because just from this condition dependence tests, and assuming that they are correct, you not learn only arrowheads. You learn directed edge. So for example, W here is a directed edge with Y, which means that W is an ancestor of Y. And Z is also an ancestor of Y. So both of them are real causes, which means that if I change the variable Z or the variable Y, I will definitely see some change on the, if I change the variable Z or the variable W, I will definitely see some change in the variable Y, right? And why there is a green error here is because there is a condition called visibility, which is going to be important later, but it's a condition that you can also read from a PEG. We call it PEG, partial ancestor graph is a PEG, that this edge is also not confounded. So for sure, I know that there's no latent confounding here. There is like a condition. If you want to know more, I can explain. But this WY, not necessarily. I know that one is a cause of the other, W is a cause of Y, but it can still have a latent confounding there. So this is going to enable me to estimate the effect, but I know the direction. So you have two steps here. And then it's called visible. And that is also something that we call M separation, which is a generalization of this separation that is going to allow me to read off this PEG, all the dependencies and independencies implied by the PEG. And the set is going to be exactly those from the true graph. So it's an encoder of all conditional dependencies and independencies, and everything that's not a circle is going to be shown because it's a complete algorithm. Okay, someone raised their hand? No? Okay. And the interpretation is like that. So circles are no invariances, arrowheads mean no ancestrality. So for sure, B is no ancestor of A. When you have a tail, is an ancestor relationship or a causal relationship, which means there is a causal path going from A to B. When it's a bidirected edge, means that it's an inducing path. We need to make sure here that it can be a very complicated path, but there's never a causal path going from A to B or a causal path going from B to A. So the way to explain the correlation between A and B is just due to a lot of latent confounding. So it's a purely spurious association. And this algorithm also allows for selection bias. So this is very common in hospital data. So you have like data that was collected in a hospital, and the hospital, for example, has a lot of reasons why a person goes to that hospital. So for example, you have a children's hospital, and then it's specialized in cancer. So the fact that the person has age, in their age range of a child, and it has cancer, it's creating a variable that's the variable that represents going or not to that hospital in particular. And since you are conditioning, when you have just a selection, so your data is just selected by that hospital, which means that you're conditioning on that variable, and that variable is not even known. So you have like a correlation between A and B, just because you selected data by condition on a particular value of some of your variables. So this means that A is just connected with B by a path where you are conditioning on selection nodes, on nodes represented by nodes representing selection bias. Selection nodes means something else. Z, so in this example, we learned, right? So Z is an ancestor of X and W. Z and W are Z is not an ancestor of X and W. Z and W are ancestors of Y, and Z is not confounded with Y. So we actually learned something in a complete data-driven way, right? There's no assumptions involved other than the tests are correct. Okay. Who asked? Yeah. Yes.
Yes, on this slide. Two questions. The difference between the M separation and D separation. It is not clear to me. And the other
I didn't explain M separation.
Sorry?
I didn't give you the definition of M separation.
Okay.
Yeah,
I thought
I'm sorry. It's like a lot of things are going to.
Okay.
But it's very similar. Yeah, I can give you the reference later. Yes.
Okay, and the other one is this the relation, the directed relation from A to B with this circle and without this circle. B non-ancestor of A and A ancestor of B. The difference between them, this is not clear to me.
Here you see that there's only one information that you can read off of this edge, which is the known invariance of this right side with the arrowhead. And usually we read like B. So all paths that are coming from, that are between A and B, and with an arrowhead. So for sure, there's no path that starts with a tail on B and arrives on A with something else, but doesn't have a path that starts with a tail. Eliminates the fact that B is an ancestor of A, for sure, because to be ancestor, you need like a direct path from B to A. So this is what's written here. Now, the second one, there is still B not ancestor of A, but now you also know for sure that A is ancestor of B. And you cannot have both because we don't have cycles. That's important. So this gives you true information. I'm just giving you the explanation of the tail, which together with an arrowhead, because if it's tail, it's selection bias. You understand?
Okay. Mm-hmm. Okay. And the last question, you said at the very beginning, there were two perspectives with observational data and interventional.
Okay. If you combine both, then you need another algorithm. There are algorithms that combine.
These are all for the observational part, right?
Yes, yes.
And for the interventional?
There exist extensions. There are extensions for many things. I think I'm going to cite some references by a few after this slide, maybe. But the idea is that interventional data gives you the right direction already. And this comes into the algorithm as background knowledge. So you can refine the search, or you can change the rules to account for that.
Mm-hmm. Okay, thank you.
Sure.
So like, I don't really get like, how do you like make these conclusions from the data? Like, how does it look like in practice? If I have Python here on my computer, how do I infer that? You know, it's like data is noisy, but
I can give you.
Yeah, it works. Sorry, yeah, like like data is noisy. Like when I try to learn something, like with a very basic machine learning algorithm, like I never get like perfect results, etc. And this looks like very, like a dream, right? Like it's like very perfect, etc. But like, how does it look like in practice? That's
I've been working with applications. I can show you in the last slide of this entire class, one presentation that I have. So you're right about being a dream with respect to this assumption. It's very, very hard to have a data set that's completely faithful. And I just submitted a paper where we have like uncertainty modeling for these tests. So you have a score. So it's now called a hybrid algorithm because you have a score and the FCI together. And then we actually account for that uncertainty. But that's the only assumption that exists here. And this is the beauty of this algorithm. There's nothing regarding strong assumptions that are not testable. And making sure that you have conditional dependencies and dependence correctly, you know how to solve. It's just get more data or model uncertainty and stuff like that. But the rules, that's why I said read the proofs. They are really simple. I'll give you one example just to make sure that. So let's see. Let me continue because I have a. No, let me try to draw here. I don't have a lecture, a blackboard, but suppose that I have a collider, just a collider. So the only structure that allows me to have independence of X and Y with Z, so X is connected to Z, Y is connected to Z, so that you found a skeleton. Then you have in your data set, X is independent of Y, and X is dependent of Y given Z. Everything else is dependent. So the only independence X. You cannot have anything, any other model that is not agreeing with that without having Z as a collider. So this part, do you understand? Okay. Now let's assume that you have a descendant of a collider. It's now 4 variables. And you learned that, let's call the descendants W. So X, Z, W, suppose that this also is a triplet that's not connected. X is not connected to W. And you try to make the test of the colliders. This is the rule 0 of the FCI. You find all the colliders. And you found that X, W, X, Z, W is a non-collider. Okay? Because X, E, and W are dependent marginally. Okay? You have several of them. Let's go back here. Maybe it's better. It's hard to, I have the separation. Sorry. I have here the descendant of the collider. Okay. This one. So if I was learning this, the only information that I have is this list. I mean, it's X independent. It's not that. I have to list more here. So it's X independent of W given Z. You see, it's a non-collider. Y is independent of W given Z. And X is independent of Y marginally. So the first time is a skeleton. So the first time that I run the algorithm, it's going to learn the skeleton. It's going to remove this edge, and this edge. So it's going to keep the skeleton exactly like here. Now I'm going to learn the arrows, the direction. So I learned that I go every triplet that's we call unshielded because there's no connection between this. So there's no shield. So every unshielded triplet, like X, Z, and Y, and I see if this is marginally connected, marginally dependent. And if it is, although they are connected, this is forming a collider. But I go to this other unshielded triplet, and I found that they are not. X is not independent of W marginally. X is not independent of W marginally. So you won't add the arrowhead here on Z because it's going to allow you to have a non-collider here. And the same for Y, Z, and W. So W is dependent of Y. W is dependent of Y marginally, right? So it doesn't fit the rule 0 where this becomes a collider. So I don't add the arrowhead. Now it goes to rule 1. The rule 1 tells me that if I have this formation, I automatically go from Z to W as a cause. Because I just told you, this is not a collider. So it's either a collider or non-collider. So it's a tail, because it's the only way to form a triplet that has the arrowhead, because I learned from the previous step, but it informs a non-collider. So it's an iterative procedure where you start with finding the colliders, then you know some of the rules are based on the fact that you don't want to find you don't want to create a cycle, you don't want to say that's a collider again, because you just said that this was not a collider, and then there is an impossibility, and you learned. But there are 11 rules to make it complete. And they are simple, really simple. Like, you just check the paper, or I can share you a few other resources, but it's something that you agree. You agree. There is the assumption of acyclicity, but this is something else that people are working on. And the FCI algorithm that I'm presenting here is robust to cycles. So you can run the same algorithm. The only thing that's going to happen is that if you have a cycle, it's going to be like a triangle of all circles. So the cycle would be there. But if you eliminate it, yeah, you can see. That's very philosophical. So yeah, a cycle, it's in my opinion, a problem of a measurement. So suppose that A causes B and B causes A, but over time, right? So A1 causes B2 and B2 causes A3 in time 1, 2, and 3, right?
Do you have like an example?
Yeah. Like, for example, people that have obesity, they have also a high blood pressure. But at the same time, people that have a high blood pressure, after some time, it have other problems that become more and more. It's really problematic. Yeah, this can be really complicated, but it's a problem over time. If you have longitudinal data, you are going to ask me, is in the right resolution? All the people are at the same time. So it's a very complicated problem to estimate, but it's a problem of statistics. It's not a problem of causality, right? Anyways, I think I need to move forward, unless there's like an urgent question here. Yeah, okay.
Maybe I missed this earlier in your talk, but can you make the independence, the conditional independence tests without interacting with the system? Just
Yeah, this is a proper. That's a statistical property. I can explain how how condition dependence works in an easy way. So suppose that you have a function that depends on, so y depends on x and z. Okay, just that. Could be linear functions. Let's simplify the problem. And I make a test if the model, the complete model where y is regress on x and z is the same as the model of y regressing only on z. Okay, I can do likelihood ratio test for that, ANOVA, very simple. Then under all correct parameters, all model specification, if these two models are different, it's because X matters. So X is dependent. If they are the same, X doesn't matter, they are independent.
Okay, thank you.
Yeah. Okay, let's move. So yeah, so when you learn a peg, I told you this represents, yeah, I need to run. So when you have a peg, this represents a class, right? So and this is important to know how to interpret it, because W here, you see it's not green, and I told you can be confounded. And the only information that I'm giving you here is that W is an ancestor of Y, which means that there is a direct path going from W and arriving on Y. So in the first example, it's a member of the class, so W is a cause of Y. But in the second example, the path is through this, okay? So I learned that W is a cause of Y, but it doesn't matter which path. It's an ancestor graph in that sense. And the problem is that I cannot say what's the direct effect, because this can be confounded, right? So this is a member that agrees with all conditional dependencies and dependence, and it's agreeing with this graph. But when you read this graph, you have to be careful. Edges can mean inducing paths, and it's only ancestral relationships. but you can still have decision making for that. I'm going to skip a bit the slides because I really want to get to the end. But yeah, the point is that you work with the class now. And you can see later, for example, like for different different true causal diagrams, you would have different graphs, but many times you can learn these invariances. So those are just examples where you run the FCI and you get it. So condition dependence tests, I just explained how it works, but of course you have like more and more sophisticated condition dependence tests being developed. So the most common one is when you have Gaussian data, then the condition dependence test is a partial correlation test. Kernel methods is still very active. So one of the areas we also saw, this is the first lecture, you want to add non-linearities there. So you can use kernels to still have the same approach, but now you use kernels. If you want to have mixture variables, the kernel also allows you to change different kernels, but you can also use likelihood ratio tests. This could be generalized linear models, but it can be any type of model, to be honest. If you have like correlated samples, so now it's becoming a statistical problem, right? So this area is very active because it's a matter of determining if one variable is correlated to another, given another set of variables. So you need to account for all types of problems in statistical tests. And this is available, so most of the packets are in R. A few packets are starting to be in Python now. I still use pretty much just R, but because I started a few years ago, and there are actually a lot of things in R, and it's hard to not be there unless you rewrite everything from scratch. What most of Python packets are actually internally is just a wrapper of R code in Python. So it's why you would do that. But that's the field, right? So developments, I want to just go over those. So the most important challenge is robustness to empirical faithfulness. And this is something that I told you that I submitted a paper. So this allows us now to have some problems in the sense that I have false negatives and false positives in these correlations tests. And it drastically improved the results. I was pretty impressed with how much modeling uncertainty of this test is actually improves, and gives you an idea, like if the final graph is actually something that I can rely on, or like the uncertainty is too high, it's better to maybe just stop and collect more data. Also, something related to abstraction. Sometimes, because these algorithms, they don't scale at all. So you can work with like 10 variables, okay? If you have, I mean, everything depends on the sample size, right? I work with medicine. Having 10,000 samples for patients is like a dream. It's almost never like the case. So that number of 10 variables works for like 10,000 samples. Of course, if you are in another domain, when you have millions of samples, this is going to be different. But a strategy that people are actually using now is to create abstractions of variables, that you basically cluster variables together using CDEX, as I mentioned. So I also submitted a paper to actually do causal discovery over CDEX. But we are here, I still assume sufficiency, causal sufficiency. It's a pretty hard work. So we have results for the latent confounding case with latent confounding, but it's not complete yet. You can also go beyond the Markov equivalence class. So for example, interventional data is a question that someone raised here. If you have interventional data, can I combine them? Yes. So there are many works where if you have both, you can combine. So very recently, Adèle, he published this paper where you can have both observational data and interventional data, even from different environments. So it's a pretty nice paper. Yeah, I won't go over this. Causal discovery with background knowledge. So sometimes you actually have background knowledge. This is something that I also work a lot with. Like I have, for example, this paper that allows you to include non-ancestral relationships. So every time that you have a non-ancestral relationship, which is the one that you have when you have experimental data as well, because you know that the direction is from one to another, but you don't know if this is so if X is an ancestor, if X is ancestor of Y, this is confounded. But Y is no ancestor of X is much easier. And in genetics, this also happens. Like, you know, that genotypes cannot be caused by phenotypes. So you don't know if the phenotype is caused by a genotype specifically, but for sure you have these non-ancestral relationships. But the problem of adding background knowledge to the FCI is still not complete. So people are just solving the problem partially, but this is still an ongoing research. I also have this paper with people that I actually met here, where we have a human in the loop approach for causal discovery under latent confounding. So we learn first a graph from data, and then we ask the best questions to an expert. What's what's your guess for this direction? Doesn't need to be correct. We can model the uncertainty. We even have now experiments with large language models. So basically you can ask the large language model, what's the answer for that particular direction? And if you have a way to measure the uncertainties, it's even better, even better. We can account the noise information here. Another thing that people works is like under linear models, you also can go further. So if you know that's linear, you can restrict the class and learn more. There's something that also people say that is an additive noise model. I know that's a function, but the error term is an additive term. So there's also a bunch of people working with that. And I also told you with cycles, especially Mui, he's working in extending everything that you learned today. It's pretty much the same, but they are accounting now for the possibility of actually having cycles. And they proved like even the FCI is still the same algorithm that you can use. And it's not going to give you the cycle, but it's not going to give you an answer that's wrong. So everything is still valid. It's just not complete under cycle. So you have extensions for time series data, which also has this, it's introducing the assumption that the present cannot cause the past. Basically, it's also a non-ancestral type of data. And I think I'm pretty much late, but so I'm going to skip this part. It's very technical, so I think it's just a way, I will go just to give you this pipeline here, which how you go from now to estimate the effect. So the classical pipeline of causality is started by expecting that you draw by hand your causal diagram, right? And if you have that, which is something that we call causal modeling, you draw it. The third input is something that you can derive, it's the observational distribution, can derive from data. And once you have that, that is something that we call effect identification task. So there's like an inference engine. There's here involved do calculus, ID algorithm, several tools. But the goal, the most important goal here is to estimate the effect of an edge. So depending of the input, which is giving you the knowledge that you know, it can have a yes or no answer. So it's a complete algorithm again. So we have the ID algorithm, for example, for causal diagrams. And the point is that if the knowledge that you input here in the graph, it's not if you have no latent confounding, you always have identifiability, right? So in the sense that you always can estimate the effect of the edges. But if you have latent confounding, this is a more complicated task because, for example, the effect of Z on X is not identifiable for sure. You have a direct latent confounding. But other edges, maybe you can estimate the effect size there. And what is the task is basically answering this probability of Y given to X, which was our intention in the beginning, as a function of just the observational distribution. So you see that there's a do on the left side, there's no do on the right side. And from a distribution, you can do whatever you want. You can take expectation and you can do whatever you want. So the point here is mapping the available distributions to what you want, which is the interventional distribution. If, of course, you have interventional distribution available and so on, this generalized, you have other algorithms to account for that. And you see that everything here is the true probability distribution, the one that we don't have access directly, but if you have data, you can estimate it. So you just go to the next step, which is estimating these quantities. So since now it's just a matter of estimating this, you just need some density estimators. and then you plug in here, and then you make this. And this is a hard task because this can be a very big equation, different equations for different graphs. But if you know this, it's just a matter of estimating the terms. Yeah, I would definitely skip a lot here. Let me go directly to to this. So there are several advances on effect identification giving a causal diagram. So for example, I told you can combine identification from observation and experimental data. So those are the reference. Sometimes the type of interventions you have, it's not a hard intervention. So when I define dual intervention, you just change the variable to a specific value, but not necessarily that's the case. Maybe you just change, there's a probability to change. So this is called soft interventions. So there's also people working on that. The general graphical counterfactual identification, which is the third layer or the third rung of the Pearl's causal hierarchy. Like you can identify counterfactuals given the graph if you have. And especially Juan is working a lot on this direction. You have algorithms that check if given a graph, you can estimate the counterfactual quantity. You also have estimation given deep neural networks. For example, so Kevin also is working a lot with that. And recently he's moving a bit to causal abstractions. But the idea here, I think it's better to give you the idea of what happens here. So if you know the graph, so here's assuming you know the graph, right? If you know the graph, you can try to fit a model, whatever model, by using inductive bias. And the model that you're going to have in the end is just one of the models of the class. However, you can see if the effect of that, one particular effect, the effect of X on Y, is changing across multiple models that could be fit to this structure and to the data. If this effect is changing, then it's because the effect is not identifiable. But if it's pretty much the same, like the threshold, I'm not sure how they define. I think there's no test yet to see what's close enough, but they consider this as identifiable and then automatically gives you effect. And they moved, if you use CDEGs instead of using causal diagrams, there's a trick because now you can estimate if the effect, identify the effect and estimate the effect instead of using the causal diagram. You use the CDEGs and then you do you can compute causal effects between abstractions. But again, the graph is given. This is very important. But there's partial identification and so on. There is also the extension from pegs. And this is pretty much important. Let me go directly to the pipeline, because you can basically replace completely the graph of the second input here. So instead of giving the causal graph, you can learn using the FCI. And there's different other algorithms now that for example, there is the adjustment criteria, and recently we have the IDP algorithm where you can have like any graph that you learn from the FCI. You can just see what's the effect and estimate the function. So it's a completely data-driven way now, because you learn the graph and then you use the IDP algorithm or conditional IDP to have conditional causal effects, and you have like a completely data-driven algorithm. And this is like an application that I told you that I would like to tell you that I actually applied this on real data. And this is submitted. We basically got a lot of bacteria data from bacteria of your gut, and we run the FCI. We made sure that this was like robust, and so this was before I submitted the CFCI paper. But we learned a graph that actually found causes. And we try to ensure that this was not just noise. So we did a lot of robustness tests, and we found that two bacteria are directly connected here with major depressive disorder. And we went further and we estimated the effect. In the case here, the effect was just adjustment. So we estimated that the more you have this bacteria in your gut, the higher is the probability of having depression. And you see that there's confounding variables. So the obesity or like your weight is the body mass index is a confounder, but we accounted for that, was part of the adjustment formula. But that was pretty much like everything data-driven. There's no knowledge imposed. And I discussed here basically two tasks, right? So it's from causal discovery or causal modeling and identification. But I also would like to tell you that the challenge, the field is big, and basically the idea is to get everything that you have in hand. So this data can be observational data, experimental data, but the idea is to model everything that you have as a causal diagram, or like a class of causal diagrams, identify the effect, and then go back, and this creates a loop that we are usually calling as the causal inference workflow, right? There's like this task that I didn't explain much, that after if the query is not identifiable, there's like a design of experiments to know which variables I should observe, which experiments I should run, to that in the next iteration I may be able to learn the causal graph or even identify the effect. Yeah, so there are many topics here you can check later. And just the last slide is that I have a lot of lectures on YouTube. They are not professional. It's just something that I found that maybe people were interested on something that I was interested. So I just recorded what I was teaching in the university. So if you're patient, you and you're interested, you can check it out. Also, all the lectures in the summer school are recorded, but I also gave these similar lectures in other summer schools. And in those summer schools, I have some material where you can run the code and do some exercises. So basically, you can just click on the link and run it. It's going to work. This is very, very basic, of course, but it's the first content. And I'm pretty happy to help you with any of your projects if you want to just make questions, or if you want to collaborate. I'm really open, and just reach out if you have interest on that. Okay, thank you. Do we have a few minutes for questions, or yeah? All right. Is there any questions?
Once again, thank you for the talk. In that publication, is there a reason why you chose BMI instead of, say, body composition from DEXA, so that you can actually separate out the effect of adipose tissue?
I work with 30 physicians here, and that's what they recommended me. I mean, it's always good to have physicians involved, and I would say the BMI was the variable that was more robust for them. They worked with that for years, and but there's like problems with the data set. For example, the variable diet, we wanted to use, but it was very noisy and not reliable. So we decided to remove it, and that's okay with the FCI because it accounts for latent confounding. So it was something that was appearing and creating confounding. The algorithm would tell you that this is missing, and the effect would not be identifiable.
Okay. Yeah, the reason why I ask is because the identification of like actually bacteria affecting depression is something that I've also observed in some of the work I've done.
Oh,
But when it comes to BMI, because it's so noisy,
okay.
using DEXA so that you can actually use the quantity of adipose tissue, that also seems to have a very positive correlation with depression. So that's the reason why I ask it. But when you look at BMI alone, it will look like a confounding factor, because even me, because of just my size and I have a more muscle mass, I'm considered to be overweight. Does that make sense?
Yeah, it makes sense, but we just hope here that in the end, this variability is going to be accounted by the tests, and if it was very variable, we try to make our best. But again, when you move from theory to applications, sometimes you need to relax a bit, and otherwise you would never go to applications, right? There's always something to think about it.
Hey, thank you very much. I think like this is very interesting, but like so you started saying, "Oh, can we like explain the real world with like this?" And I started to think, oh well, this is like really interesting because one of the questions that I always have is, can I understand how the human brain works by understanding language models? So, you know, like if I understand how they work, does that tell me something about like how our language works as humans? And I started to think, oh yeah, oh maybe this is the answer. You know, maybe this is like what we actually need to understand, like how the brain works. But like the problem that I see here is like language model. You know, like you can't build a language model with two neurons. And here we're always having like I don't know, 8 things at most, right? Like we have billions of like parameters, etc., when we have like a language model. So like the problem that I see here is like like it's like a maybe like a nice idea, but like it wouldn't really explain the world, right? Because like it needs to scale and like everything I see here, I don't know, like how do you feel about like the future of this, right? Like so AI was able to scale because we had like parallels.
Yeah, I mean, it's known that the causal discovery is a super exponential problem. It's a NP hard problem unless you make assumptions. And those assumptions don't necessarily are the assumptions you want. So in terms of explaining the world, it's really hard because I don't know if you really need all these variables to explain the world. So what the field is right now trying to do is what I told you about causal abstractions. So maybe if because what is causal abstraction is not just grouping variables and that's fine. It is actually making sure that all the causal relationships are preserved. So even though I put all these variables together, I need to make sure that they are put together in a way that I'm not losing information and they are preserved in the right direction. So the way to scale right now, that's the direction to go. Like you convert your model from the low level perspective to the high level perspective, and you try to understand the world in this high level perspective. But that's very far from being applicable. Unfortunately, I'm working on that. So as I told you, like I submitted this paper with Tara and we worked pretty hard, like for 2 years now. And the best we could do is like, let's assume cause sufficient and do something here because it was very hard. Like we never got to the end, but it's something that maybe we'll have in a few years. And this would be very helpful because then you can basically learn a graph that has a very high level description of how things work. And brains are like that, right? So you have like a billions of neurons in your brain. Not necessarily you want to know how one neuron causes the other. If you understand how maybe the areas are connected in a causal relationship, if they are related in a causal. So there are many fundamental questions here that what's the right level of abstraction that we can understand reality? Especially if you don't know what are the variables as in large language models, right? You don't know what are the abstractions involved. If it's like grammar, if it's like sentiment, if it's like intuition, if it's visual. There are so many things and they are all abstractions. So it's necessary. It's a step really required to scale is to understand how to do causal modeling in the abstracted way. And but at the same time, you need to, for example, these algorithms, they are completely brittle, like in low data regimes. So uncertainty modeling was something that I noticed in practice that, okay, this actually was the paper that I said, okay, it's so unstable that I had to put a lot of these tests because I wanted to have some application before working on theory again. And in the end, I said, I cannot stop. I really need to go and improve the technique. So everything needs to improve a bit, but we are getting there. So there are many fundamental problems where people just need to think and solve. And when we put everything together, maybe we'll be able to scale to large language models. But this doesn't prevent you to work on like maybe small models for language, or like maybe try to go back a bit and try to understand how humans act in different scenarios. Maybe this translates to language. Yeah. I think we need your creativity for that. Yes, sure.
You can.
What is the minimum number of observations that you recommend to use these methods?
Yeah, in structure equation modeling, you're feeding a linear model and you just need the parameters and you don't have latent confounding. You have, yeah, that's not the problem is that the search, right? So why FCI is a super explanation is because you need to test all pairs of variables, giving all possible condition dependence tests. And if you want to do uncertainty modeling, as I did, you actually need to run different tests to model that. You have to go to Bayesian inference, and this takes more and more time. And at the end, you may end up with a list, and this actually happens many times. Like you don't have only one output, one peg at the end. You have a list of many pegs that are not significantly different, given that they score. And at the end, you have nothing, because if they are flipping in this list of all, so basically you have to stop and say, okay, I need more data. But sometimes you have it. Sometimes you are lucky, and with 4 variables, you learned something. This is what happened in this application. So we started with 300 variables in our gut, and then you do statistical association analysis just to filter those that are really strongly correlated to depression. And you already eliminated 200. And after that, you see, okay, maybe let's start with the most significant ones. Like let's put, like this is what we did here. We corrected the p-values and we started with the 4 top ones. It's not a problem when you are accounting for latent confounding, because you can just, okay, they may be important, but let's see if the first 4 helps. And you learned, I learned. It could be the case that I couldn't learn and that I would have to increase the number of variables. But then it's getting more and more hard to make sure that the tests are all correct. And if you model uncertainty, I would say I would get probably many possible solutions, and maybe I would not be possible with more variables. But this was a lucky case. Applications are hard because of that. You maybe try, spend months filtering data, cleaning data, doing robustness tests. At the end, you have nothing because the data says I have no evidence for saying that. But that's a good thing, right? We want good results. We don't want just noise. I think that's a good science.
I have a question here. Yeah, thank you for your talk. I've seen Bayesian networks being used in forecasting. So you're forecasting in the same sense as forecasting in prediction markets. So trying to predict things like, will there be a third world war in the next 5 years? And here I think the Bayesian networks are mostly drawn by hand by people who they draw the causal relationships and they attribute probabilities to each other, to each of them. Have you seen or worked in this area, or there's basically no data to learn these kind of relationships?
I'm not sure if I got your question. Like Bayesian network learning, it's just like if you're learning, if your goal is prediction, there's no problem of putting a Bayesian network there and maybe get a graphical model for prediction. You can. The problem is like he's saying that graph that you learn, the Bayesian network you learn is causal, because you have many Bayesian networks that are equivalent. And so the problem there probably is like they try to predict the forecast, and that's it. They don't want to do causal inference there. And here we don't learn the graph, right? We don't draw the graph by hand. We can learn through causal discovery. And what causal discovery does is exactly that. We know that there are multiple Bayesian networks that could fit the data equally. So we want to learn the invariances across these Bayesian networks, not to do prediction, but actually to make sure, to first interpretability, to know exactly the invariances, and you can actually say that this is from the world, because it doesn't matter, it's always like that. And second, to effect identification. So you get one, you estimate what's the quantity after, like what's the effect of a variable on another after an intervention. So this is help you to optimize, like to get optimal decision, to make optimal decisions. So you know which value of X is the optimal to have like the best performance to Y, and you know exactly what's the best treatment.
Yeah, exactly. So
this type of things.
like in the extreme, like they would draw everything by hand and do this, but you could also learn part of it at least, right? For the part.
No, in this thing here, like in the pipeline that I told you here, this one, there's nothing driven. There's nothing like you learn everything. So this peg you learn from FCI,
Yeah, I understand.
and this is you just giving the peg. That's it.
Yeah, I was wondering if you've seen something applied to this kind of domain where you have
Ah,
a
okay.
broader thing that you're trying to predict, or trying to predict it. You don't have data to do, but maybe you can divide the problem into subparts in which some of them are. You can do these kind of things instead.
Yeah, for weather forecasts, there's like Jakob Hunke. He's working a lot for like this extensions to time series data, and he works exactly with climate data, and they are doing a lot of stuff. It's a hard problem because the dimension is still high in the past. So if you ask me if they are getting the right model, I don't know. There are assumptions in their statistical tests.
Yeah.
Again, we are moving here from causality to statistical tests, and you can have problems there.
Okay.
Yes. Yeah. Thank you.
I know it's going to be around for the rest of the day. And
Exactly. Yes. Yes. So I'd be glad to take questions.